So I just want to recall where we arrived at the end of last lecture. We begin with a polytope. So we're almost always assuming that this is the simplicial D-polytope containing 0. And we had this very basic question. So what I tried to impress upon you is the fact that our knowledge of polytopes in high dimension or even dimension 4 is still very partial. And a basic thing that we can do is ask how many vertices, edges, faces, etc. a polytope can have. So we get this list of numbers, F0, F1, F2, F3, F4, and we can ask very simple kind of basic question about polytopes. What lists of numbers can occur? And what I want to explain now is McMullen's conjecture, which is a conjectural answer to this question for simplicial polytopes, which is proved via Hodge theory, and also gives us access to the one example of Hodge theory just beyond geometry. So we have this list Fi, and we count in a somewhat funny way. So we build the following polynomial. And another way of saying this polynomial is we consider the corresponding fan corresponding to this polytope. So every vertex describes a ray, every edge describes a cone of dimension 2, every two-dimensional face determines a three-dimensional cone, etc. And we do this, we write down this polynomial. And if you know toric varieties, the meaning of this polynomial will already be very clear. But I kind of deliberately obscured the meaning of this polynomial last time, and it will become clear now in a second, okay? And then, so this is just a repackaging of these numbers into this so-called H vector. So from F vector, we get an H vector. And equivalently, it's easy to go back. If I know a list of H vectors, I can just do a simple transformation to produce a list of F vectors. And we also saw via this rocket ship journey that HIs count the maximal dimensional cones with a particular statistic, which is basically something to do with where they appear in this rocket ship journey. Okay, so that was the summary of last week, not last week, Tuesday. So I want to, in the words of Monty Python, and now for something completely different. So we have C, a finite dimensional algebra. So this is a finite dimensional algebra, finite dimensional graded algebra. And also, please yell at me if I write too small. Graded algebra over R. And the very important assumption is that C is generated in degree 1. Okay, so C is generated in degree 1, and then we can form its Hilbert polynomial. We can look at the dimension of the ith graded piece and count it and form a polynomial. I equals 0, I is bigger than or equal to 0. It's a polynomial because it's a finite dimensional algebra. And there's a very beautiful theorem, I think essentially of Macaulay, but if you're a commutative algebra expert, you can, I think this is Macaulay, and then maybe it wasn't, I think that he basically had the complete answer, but maybe he didn't say it in the nicest possible way, and then this was reinterpreted several times, is a complete characterization of these polynomials. So Macaulay gave a complete characterization of which polynomials occur in this way via a family of inequalities, via a family of inequalities. So a very simple inequality that you can see is because it's generated in degree 1, there's some binomial coefficient that tells me a bound for the dimension in degree 2. Yeah. If I have one generator in degree 1, I certainly can't have more than dimension 1 in degree 2. If I have 2 generators, I can't have more than 3 dimension in degree 2. And now, if that number drops, there's a relation which then propagates higher, and you can start to imagine that there's some list of inequalities. And this is called these are called M vectors. I think after Macaulay. Okay, so polynomials like this, equivalently the list of this vector of dimensions is an M vector if and only if it satisfies this finite list of inequalities that's very checkable. And equivalently, there exists a graded algebra of this form. Okay. Now, McMullen's conjecture says the following. So we start with an F vector. Now, it says that there exists a simplicial polytope P with F vector F. If and only if. So from F, we've explained there's a purely algebraic way to produce H. So the first condition is the condition that we basically already proved yesterday, which is I equals HD minus I. So there exists a simplicial polytope, simplicial D polytope. This passage depends on D, as you can see up there. So this is, and these are positive. So this is called then Somerville. So these are the equality parts. And as I said, these kind of date back to the early half of the 20th century. And then McMullen's innovation was to say that if we form GI, which is HI minus HI minus 1 for all I less than the floor of D over 2, so this is, so we go, it's a funny use of the alphabet. We go from F to H to G, okay? But such is life. We form this G vector, and then the second condition is that the G vector, so G0, G1 is an M vector. Okay. Now, I'm not an expert on this subject, but my impression from reading McMullen, when you read McMullen's conjecture, he forms these GIs, and then he writes down some kind of crazy list of inequalities involving binomial coefficients. And I think it was Stanley that realized that this list of inequalities is exactly saying it's an M vector. Okay, so I just want to kind of impress upon you the remarkableness from a kind of combinatorial point of view that occurred when McMullen wrote down this crazy list of inequalities. You know. Okay, so yes, we will see that in just a second. Yep, yep. Exactly, H minus 1 is 0. Another kind of interesting thing here. So, you know, this looks Hard-Lefschetz-like. And we'll see that this is very much coming from Hard-Lefschetz. The other thing that's interesting here is that these Dean-Somerville equations are kind of a Poincare duality type statement. But this is a very distilled, so this only has half as many numbers. And so what we'll end up seeing is that we have this big cohomology group, and then these GIs are basically the kind of primitive cohomology of this thing. And so this stuff is concentrated in half the number of degrees. And so this G vector is an incredibly efficient distillation of these very complicated face numbers. So if you actually do an example of this, if you work out a big polytope, you'll see these enormous F vector numbers. And then you do H, and they're a lot more manageable, but they're still rather complicated. And then G, you can often write down like there'll be 1, 2, 3, 4, 5, 6 or something. Okay, so it's a really beautiful, simple distillation of what is the guts of the polytope. I mean, in the assumption that it's an M vector, I'm saying that they're positive. So, part of being an M vector is this should be a positive list of numbers. Okay, so just as an application, I want to, this is just an amusement, okay? So we're allowed to have some fun in life. So are F vectors unimodal? What you could do is you could write a little program to generate 1,000 random points in R20, and you could use one of the many libraries, polytope libraries on the internet, and compute how many facets there are. And your computer would do this pretty quickly. And you could plot what F minus 1, F0, all the way up to FD. And what you will see, almost certainly, is something that looks like this. Okay, so it appears to go up and then down, and that's called unimodal. And there's various theorems. So combinatorialists really cared about this in the 60s and 70s. There's various theorems that tell you that it goes up to halfway, and then from 3/4 it goes down. Okay. And then there was this mystery about what happens here. And the answer is yes, below the dimension 19. No in dimension 20. And the first example has more than a quadrillion vertices. The first known example has vertices, and there's an example in dimension 30 with 1,000 vertices. Okay, and this kind of looks amazing, but if you think about it, it's actually kind of a little bit of a cheat, because you can just write down G vectors. You can, like, it's very cheap to just generate examples of G vectors, and then you can like go back through this whole procedure and then get the F vectors and see what they look like. Okay? And so you don't actually ever have to construct a polytope, because if you're actually going to try to construct a polytope with a quadrillion vertices, good luck. Yeah. And it's really remarkable how subtle. So there's this beautiful book by Günther Ziegler called Lectures on Polytopes. And he gives the face numbers of this crazy example. And there's a tiny, tiny drop. Like it goes a tiny, tiny little bit down. Very subtle. Okay. So now we come to toric varieties. Are there any questions on this? So that's kind of part of, yeah, that's kind of encoded in there, but so C0 is R. Yeah. Are all F vectors realizable? Sorry, I'm blanking on what you're asking. Can you say it again? Are all G vectors are M vectors? Yes. Yes. Yeah, and I think it's secretly hiding in this theorem. So maybe so I know roughly what speed to go at the current point. Can you put your hands up if you are very comfortable with toric varieties? Can you put your hand up if you've seen the definition and cones and fans mean something to you? Okay, awesome. And yeah, I won't ask the other question. So there's this amazing dictionary. From rational polytopes to toric varieties. And I just want to go over what I need from this. So we have T C star to the M, and then we can consider the co-characters of T and tensor this with R, and this I call V. And now, based on the response to that last question, I think I'm okay if I say a fan. So this is a collection of cones satisfying some conditions. We associate a T variety. So we have a picture like what I've been drawing. So I'll just say verbally a little bit more detail so that we're on the same page. So we start off with the notion of a cone. And if we dualize, so a cone should be pointed, rational, and polyhedral. So this means it's pointed, so it strictly lies in a half space. I'm not allowed a cone like, no, I'm allowed a cone like that. I'm not allowed a cone like that. Yeah. So it's pointed, rational, polyhedral. It's generated by finitely many rays. I dualize that cone, and I get the dual cone in the dual vector space, which is the characters of T. And if I look at all the integer points in this gives me a monoid, and this generates an algebra. I take spec of that, and I get an affine toric variety. So for each of these cones, I have a toric variety. So for example, this one, if I dualize it, I get everything. Now, when I take spec of that, I get exactly functions on the torus. So this corresponds to So this toric variety has a stratification by the interiors of the cones. So this would be a GM squared living here. This would be a GM living here. And here I'd have, so the maximal cones corresponds to the fixed points. So I get a T variety X sigma. And this has a stratification via sigma in the fan of GM to the D minus the dimension of sigma. Okay. And this fan is complete. Complete in the sense that these cones cover the whole space, if and only if X sigma is complete. And if I do this procedure where I start with a rational polytope and take the fan over it, I get a projective. So fan over a polytope. No, not projective, complete. Complete as an algebraic variety. Aren't I allowed to say a variety is complete? Is that not a word? Proper, sorry. Is it classical terminology? Okay, so I'm still allowed to use it. Proper. Yet more evidence that I'm becoming an old man. Fan over P. So if we take a fan over a P, a rational polytope, if and only if projective. Okay. So another beautiful, like, basic thing that you can, for example, read about in Fulton is that not all cones are of the form. I mean, in 2 dimensions they are, but in 3 dimensions you already examples. Not all cones are fans over polytopes. And if you are a fan over a polytope, if and only if your proper thing is actually projective. Beautiful. And simplicial, this is very important. So, I mean, everything here is important for what I'll discuss in a second. So simplicial, if and only if. So simplicial means that every cone is spanned by a Q basis. Sorry, every maximal cone is spanned by a Q basis of my space. Okay, so I'm not allowed a cone, for example, in 3D that has 4 rays coming out of it. Simplicial if and only if X sigma is Q smooth. Okay. So this is the topological thing that we need, i.e. that rational numbers thinks this is a smooth variety. But algebraic geometry, this just means it has finite quotient singularity. So remark, can you see the singular points? Mm-hmm. Yeah, you know, it's like you take your thing, you take minimal vectors of the ray, and then you compute like a co-kernel of some map defined over the integers. This gives you a finite abelian group. So if we count the points of X sigma over FQ, we get sum over sigma, a cone, sorry, that should say cone. Oh, sigma in the fan, yes. So sigma is a cone, Q minus 1 to the D minus the dimension of sigma, which is exactly that thing. So this is exactly the H vector. Okay, so this mysterious transformation in polytope land makes total sense in toric variety land. We're just computing the point count. So the H vector is the point count of the corresponding toric variety. And just some examples. So if we started with this polytope, we would get this fan, and then we would get P2. So we get 1 plus Q squared. Another example is if we started with we would get the projective cone over P1 times P1. And this would have, if we count points of a projective cone, we get Q times the original point count plus an extra point. So we get 1 plus 2 plus 2Q squared plus Q cubed. So we see that this doesn't satisfy Poincare duality. What's going on? It's not simplicial, yeah? So that answers this guy's question, who's currently writing from yesterday. So this is, we see that the H vector does not satisfy the Dehn-Somerville equations as soon as we're not simplicial, yeah? Okay, and lastly, the rocket ship journey gives rise to, I won't exactly explain how due to lack of time, but it gives rise to a cellular decomposition of the corresponding toric variety. So we get empty set equals Z minus 1, inside Z0, inside Zn, which is X sigma. So here it's extremely important that P is simplicial. Such that Zi take away Zi minus 1 is isomorphic to A, the Di, where Di has a very similar meaning to in the rocket ship journey. And so this is the cell decomposition, and this implies that the, you could also deduce it from other means, but the Hi is the dimension of the 2ith cohomology. So I promise to always use real cohomology and cohomology with real coefficients, and I'll stick to that convention. Okay. So now we can give the proof of the that direction of the, so Stanley's proof Okay, so what we want to say is that starting from a polytope, we form this H vector and the G vector, and the G, we want to prove that the G vector is an M vector. Yeah? So I'll explain two ways to see it. The first way is whenever you have a cellular decomposition of a variety, the fundamental classes of the closures of these guys give you a basis for your cohomology. And that's a simple argument using the long exact sequence of cohomology. You add your, it's like in topology where you're just adding a cell one by one. You don't have any boundary maps because everything's even dimensional. Okay? And then you just need to work out what this DI is and see it's the same quantity that we saw in the rocket ship journey. Okay? Another way of seeing it is up here. This is rationally smooth, and so its cohomology is pure. And so basically these counting points computes cohomology. Like you can read off the point counts, the rank of your cohomology groups. Yep. So that's the kind of high concept explanation. That's the low concept explanation. Yep. And just for those that know this business, so if you have a polytope, so the rocket ship journey, we decided this direction in our rocket ship journey. And what's this direction? It's a co-character of the torus. Yep. So this is a vector in the co-character lattice of the torus. In other words, it's a map from C star into the torus. And now what I can do when I have a C star action on a smooth variety is consider a Biriniki Birula. I just have to say it fast so you realize I don't know how to say it. Decomposition. Yep. So this means that, so this torus action will have fixed points corresponding to the maximal dimensional cones. And then I can look at the attracting cells, and this will exactly give me this decomposition. Yep. So my rocket ship journey is secretly the BB decomposition. Yep. So Birinitsky-Birula recently died, I think about 3 or 4 years ago. And there's a beautiful obituary you can find to him on the internet if you search. Okay, so how do we prove this direction? So just before I go into this proof, we shouldn't forget that in order to prove a theorem, you need to prove both directions if it's an if and only if. And this is, I've never looked at, and it's by Billera and Lee. And Stanley says it's ingenious. But no idea how to do that direction. You actually have to construct a polytope. So we begin with our P, and then we can associate our fan, and then we can associate our X sigma. And this comes equipped, because we started with the polytope and not just a fan, with a canonical ample class. And Hard-Lefschetz implies that multiplication by omega from Hi of X sigma to Hi plus 2 X sigma is injective for I strictly less than the floor of D over 2. Okay. So Hard-Lefschetz says more than this, but it definitely, I can't factor through, I can't factor an isomorphism through something that's got a kernel. As I go up to the middle, I have injections. So this tells me that if I form the cohomology of X sigma modulo the ideal generated by W. This is finite dimensional algebra. With Hilbert polynomial the dimension of that minus the dimension of that. So the Hilbert polynomial equals the G vector. Okay. So we're done if we know that this is generated in degree 1, and that's pretty easy to check. So it's also, this will be an exercise at the end of this lecture. It's really not difficult. So the cohomology of X sigma is generated in degree 1. So here's our yeah, so there's something to do with a factor of 2, yeah. With Hilbert polynomial divided by, with degrees divided by 2 equals the G vector. And that's it. Okay. So hard Lefschetz was used in a crucial way to establish the existence of this algebra. Yep. Yeah, so rational. That's exactly what I'll discuss now. Did you have a question? Yeah. Yeah. So this is the algebra that proves that it's an M vector. Something is an M vector if and only if there is a finite dimensional graded algebra generated in degree 1 with Hilbert polynomial, the thing that you wanted. Yeah. Yeah. So this list of numbers satisfies these inequalities. Mm-hmm. That is exactly what I'm talking about now. That's exactly what I'm going to talk about now. If we replace, so in this world of simplicial, intersection cohomology is just normal cohomology. But if we take a general toric variety, take intersection cohomology, then so there's a way to define the Betti numbers combinatorially. This is called the generalized H vector. And so one thing that's bonkers is if I take a non-rational polytope, the cohomology ring is not combinatorially determined. So the cohomology ring of the polytope really depends on the particular realization of the given combinatorial type that I've taken. Kind of shocking to me. But the intersection cohomology does not. The intersection cohomology is a combinatorial invariant. It's given by this generalized H polynomial. People like me love this, but polytope theorists not so much. Yeah, because the generalized H polynomial doesn't have a clear meaning in the world of combinatorics. Yeah. So I'll also maybe discuss this briefly if I have time at the end. So what about non-rational P? So firstly, I just want to say the following. I don't want to write it. So this was what Mirko was mentioning. If I have P non-rational, and simplicial, I can perturb the coordinates. And remember that I said that simpliciality was an open condition on polytopes. So what that means is that if I move the vertices a little bit so that their coordinates are rational, I won't mess up my polytope. So I get a P prime, which is rational, and the same combinatorial type. And now I can run the same machine. Okay, so Stanley proved this conjecture for all simplicial polytopes, whether or not they're rational or not. But I hope you agree that it's not particularly natural to perturb my coordinates. Sure, I can prove a theorem like this, but still there seems to be something interesting there when my coordinates are not rational. Okay. And the second thing is that if P is no longer simplicial, I cannot do this. So there's polytopes which are not realizable over Q at all. Okay? So if I want to be in this generalized H vector world where I consider intersection cohomology, there's genuinely new stuff that shows up for non-simplicial polytopes, non-simplicial, non-rational polytopes. So firstly, I want to explain how to produce the cohomology ring and how to even make a statement just beyond geometry. So we go back to P rational and simplicial. So if we consider the T equivariant cohomology of a point, this is canonically, so this is the cohomology of the real cohomology of BT, which is canonically the symmetric algebra on the characters of T, which I can also see as being the polynomial functions on V. Now the localization theorem for equivariant cohomology tells me the following, that the T equivariant cohomology, so maybe, I'll just give you 2 seconds on equivariant cohomology in case it's not your world. So this is defined to be the T equivariant cohomology of X times T over ET, where ET is the classifying space of T. And this has a map to cohomology of point times T over ET, which is BT. So this map induces a map back in the other direction. So this is a module over the equivariant cohomology of a point. Okay. You might say cohomology is hard enough to compute anyway. Why am I making it so much more complicated? But it turns out that somehow viewing, if you take ordinary cohomology, it's just an algebra. But if you take equivariant cohomology, it's a module over a polynomial ring, and so you can start using techniques from commutative algebra, and this is extremely powerful for actually doing computations. So there's many things that we can compute only because we first compute equivariant cohomology and then somehow deduce ordinary cohomology out of it. And here's an example. If we take the T-equivariant cohomology of our corresponding toric variety, so we have P rational simplicial and we have our fan, then this is a beautiful exercise in the localization theorem, piecewise polynomial functions on sigma. So what does this mean? This is a set of F sigma over the, so let's just call this ring R, polynomial functions on V, is over the maximal dimensional cones such that, so the picture is, here's my fan. I have F sigma prime. These are both polynomials, and I want them to agree whenever these two these two cones in. So I only want to consider functions on the polynomial functions on the maximal dimensional cones, and I want them to be equal when their intersection is codimension 1. So F sigma equals F sigma prime on sigma intersect sigma prime if sigma intersect sigma prime, if the dimension of this D minus 1. This is what it means to be piecewise polynomial. Okay, so I have polynomial, 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 polynomial. They agree on the codimension 1 faces. Another way of saying a piecewise polynomial function is a function which is continuous and is given by polynomials on every maximal dimensional cone. So that's localization theorem part 1. So maybe it's useful for the people that have seen the localization theorem before to see why this is not kind of falling out of nowhere. So the localization theorem says that in nice situations, of which this is one, the equivariant cohomology injects inside the equivariant cohomology of the fixed points. Now, what are the fixed points? They're exactly these maximal dimensional cones. So that means that the equivariant cohomology injects inside this product. So a polynomial here, a polynomial here, a polynomial here, a polynomial here, a polynomial here. Second part of the localization theorem describes the image. It says that for any codimension 1 subtorus, I can consider the fixed points under that subtorus. I have a map, and the image is described as the intersection over the images of all those maps. So a codimension 1 subtorus exactly with an interesting fixed point set corresponds exactly to one of these codimension 1 faces. I have this, the fixed points will be a beautiful P1 here, together with a whole lot of other isolated stuff that doesn't do anything. And then when I expand what this cohomology of P1 says, it tells me they should agree on this intersection. So the second part says that is ample if and only if it's strictly convex. So this means, so roughly speaking, if I think about P1, so here's the fan of P1, strictly convex says, so now, what's an element in degree 2? This is something which is piecewise linear. So strictly convex says that it's something like this. Okay, it's not allowed to be, you know, this one's allowed to go down to here, but it's not allowed to, it's got to be here or something. So, and if I think about in dimension 2, it says that I kind of lift up my fan all around. So strictly convex says that for all x not in sigma, f of x, sorry, is bigger than f sigma of x. Okay. So as I cross any of these walls, I tilt up a little bit. And 3, the ordinary cohomology of x sigma is this T equivariant cohomology modulo m, where m is the ideal generated by a positive degree elements in R. Okay. So another way of saying this is that the ordinary cohomology is obtained from these piecewise polynomial functions by modding out by all globally defined polynomial functions. Okay. And then the really important point is that this makes sense for any polytope, rational or not. Okay, so we get so we kind of get the T equivariant we get A of P, the piecewise polynomial functions on the fan of P. And we get the cohomology in inverted commas of P. Which is A of P modulo M. And so this is the second instance of Hodge theory just beyond geometry, in that Hard-Lefschetz and the Hodge-Riemann relations hold for the cohomology of any polytope, any simplicial polytope. So theorem. McMullen, Hard-Lefschetz, plus Hodge-Riemann This is simplicial. And so McMullen's proof. So my, as I keep saying, I'm not an expert, but my impression is that somehow McMullen was, delighted that Stanley has proved his conjectures, but a little bit annoyed that you need to know all of this crazy stuff from Deligne and stuff like that to know that his conjecture is true. And so he was like very, very much wanting to have a combinatorial proof, and he found one, and it's pretty. I mean, it's very ingenious, but it's also difficult to read. And there's this very beautiful paper of Fleming and Carew. Give excellent explanation of McMullen's proof. Okay. So I'm almost out of time. I just want to say the key idea, because it's also the key idea in our work with, so it's the, yeah? The reals. My coefficients are always the reals. Are there any more questions? It's kind of beautiful now, yeah? Yeah, that's a really good question. Yeah, if I had another kind of 10 minutes or something, I could tell you what the evaluation is on the top on, so what the trace is, and then you would have the pairing. I just don't quite have enough time. So I just want to kind of, let me just comment on these summer schools in general. So I think that there's like different levels that you can get out of these things. And one of them is just to like have little slogans where at some point, if you need to learn something, you have this little slogan in your head that's helpful. So I remember Reinecke gave these really beautiful lectures on GIT when I was a graduate student. And I thought, I'm not doing GIT, I don't really care about it, but somehow the idea that you chuck stuff away and then form a quotient is very useful. And that's what I got out of his talks. Yeah. And then later on, when I tried to learn GIT a little bit better, it was like very useful to know, okay, I need to work out that I chuck stuff away and then form a quotient. And that's my like roadmap through these mountains that I have to navigate. Yeah. But I also want to emphasize that I feel like really grabbing hold of a course is also very important. So I really hope that some of you have actually tried to do one of the exercises that you can't immediately see how to go do or something like that. Yeah. And I'm a little bit surprised at how few questions we've gotten. But anyway, let's see. Yeah. But just as a general point, like slogans are also useful. Yeah. And so the key idea is a slogan. So this is an idea that I first learned from the work of Di Cataldo Migliorini. Apparently, he said he learned it from, so Luca said he learned it from Claire Voisin. I have no idea who Claire Voisin learned it from, no idea where the genesis of this idea is. It's a very, very beautiful and powerful idea. The idea is the following, so this is just slogan. Hard Lefschetz plus Hodge-Riemann in dimension d-1 implies hard Lefschetz in dimension d. Okay. So basically, if you want to establish hard Lefschetz in dimension d, you want to establish that some map is an isomorphism. You reduce to the fact that that a certain form on a certain space is non-degenerate. Now, you've got no hope of showing this until you realize that that is a form on a space. It's a restriction of a form on a bigger space, and this form is definite. So the restriction of a definite form to a subspace stays non-degenerate. That's the crucial thing. That's how you get this. And so you can do these inductions where you say, okay, I know hard Lefschetz and I know Hodge-Riemann in dimension d-1. Now I know hard Lefschetz in dimension d. And now all I'm missing is Hodge-Riemann relations in the crucial middle degree. That's where everything takes place. This is where the Hodge conjecture takes place. This is where everything takes place, in that crucial middle degree. And then you work like hell to get the signature right in that middle degree. And then you can crank your handle and continue. Okay? That's the slogan. And this is beautifully explained in Kalekaru. And if you want to know what this key idea is, I would recommend like the work of De Cataldo Migliorini or this paper. So in polytope land, it's really beautiful. You know, there's about a page giving this idea. So they get this, and then you do like simple movements on your polytope called flips, and you analyze the sign change through these flips, and this gives you your Hodge-Riemann relations. And I just wanted to finish with an exercise. Prove that AP for any polytope, any simplicial polytope, so P is simplicial, is free over R. Okay, and the hint is rocket ship. Okay, so the way that you get a basis for the cohomology is via Berinsky-Birela decomposition, and you can give a precise combinatorial analog of this and prove that these piecewise polynomial functions are free. Super beautiful. And two, prove that AP is generated in degree 2. Okay, so this was the missing statement, the statement that I didn't explain in how to deduce the M vector business. So tomorrow I'll change direction and discuss these Lorentzian polynomials. Thanks.
Thank you very much. Are there any questions?
Can you formulate Macmillan's conjecture when P is not simplicial? I mean, I don't understand what you can put instead of the algebra. I mean, what is an M vector in particular?
So what you can see easily is that, like in that example that I gave, the cone over a square, everything breaks just for piecewise polynomial functions. So this is no longer free. It's all very complicated. Yeah? But now there's the story goes like this. You start off with your toric variety, and then if you think hard enough about it, so there's this work of Knaup, Wiesner, I can't remember the names, and also Bernstein-Lunds, who explain how to produce a module, which is the equivariant intersection cohomology of your toric variety, okay? By some inductive, like basically commutative algebra kind of construction on your fan. So you start off. So let's say that we're in this setting. So you start off on the middle and you put R. And then you slowly extend R. So R, sorry. So we start off with the constant sheaf on the open bit, and that's our open bit. And so we put R here. And then slowly you move your way out and you do some construction, some computation of projective covers. And basically you put a projective cover of here, here, and here, and then you compute another projective cover and go further and further down in your toric variety. So you get a whole complex of modules on your fan. And then there's a procedure to take global sections of that. Yeah. So you produce a module and you produce a trace map on it. And this is the intersection cohomology. So now you can formulate hard Lefschetz, you could formulate Hodge-Riemann. And it was a big mystery for about 15 years whether hard Lefschetz and Hodge-Riemann are true. And that was proved by Kalakaru. Again, using that idea, but it's much more complicated now. Yeah? And so that, we know that the, to any polytope, you can associate kind of intersection cohomology groups. And these are genuinely, like, this really does go beyond geometry. Yeah.
This cohomology of the polytope are honestly different from the cohomology of the toric variety?
It depends what you like in McMullen's thing.
Yeah.
Are you talking about simplicial polytopes?
Exactly.
Well,
Real.
Yeah, I mean, I would say that they're slightly different in that their kind of structure constants, for example, aren't rational. But I think that you could probably argue that they're like a deformation of the actual cohomology ring over Q or something like that.
So there could be a proof also of that using this deformation?
Probably. I think that's a really interesting question, and I did think about that a bit, but I don't know. I don't really know how to formulate the deformation business.
In the application of this key idea to this polytope business, is there a Lefschetz hyperplane theorem present?
That's a really beautiful question. So in the key idea in geometry, you go, I have an ample class, I take a generic section, everything's honky-dory. Yeah? In combinatorial land, you've got a problem, because if you take a generic section of a toric variety, it's not going to be a toric variety. So what do you kind of do? So let's say that this is our toric variety. Yeah, so it's a great, so just like this arrow is basically weak Lefschetz plus source. That's very important. That's basically where your question is coming from. So think about this toric variety. So it's got this C star, and then it's got these toric P1s on the boundary. And a generic hyperplane section, looks like this. Nothing like toric. Yeah. But what I could imagine is maybe I can degenerate this dude to the boundary and get something toric. But now it's not going to be smooth anymore. And that's basically how these, like, that works. And yeah, that works, and it's a bit subtle. And that's exactly what happens in Ben and my proof in Zirkel bimodule world. We again can't take a generic hyperplane section. We again have all these Schubert divisors on the boundary, and we can degenerate to them, and then everything works. Yeah. So maybe for algebraic geometries, it's like a good thing to keep in mind that, like, when you're doing weak Lefschetz, sometimes you can take very bad-looking sections of your ample class and still hope for something reasonable.
Thank you. Other questions? If not, let's thank Geordie again. Okay, so we'll continue with Jochen's third lecture on geometry of moduli spaces of Higgs boson.
Yeah, thank you. Welcome back. Okay, so as promised today, I want to switch gears and talk a bit more about the geometry of this moduli space of Higgs bundles. And so the key, I will try to recall what it was and give you so the key player is Hitchin's morphism. which is usually called H. And so it's a map of moduli spaces. So this Dolbeault moduli space were vector. So we fixed the curve. We took a vector bundle on the curve, and we took a Higgs field. And for today, so last time I wrote it as a section of the endomorphism bundle. So let's just spell out what it means. A section, and we look at this moduli space. So if I put angled brackets, I alternatively mean the moduli stack of objects or the moduli space. So it's the moduli space of this was this Higgs bundles. At some point I will put a semi-stable again, but for the moment it doesn't matter. And then Hitchin observed that if you give me such an that he can produce a functions on this moduli space, and how do you produce a function out of this? So you get a morphism to an affine space, which is called the Hitchin base, which is the direct sum of global sections of tensor powers of the canonical sheaf. And what's the morphism? You take e comma phi, and you take it to the characteristic polynomial, the coefficients of the characteristic polynomials of phi. And so if you want to be explicit, so what you do is, well, if you can take the traces of the exterior powers of phi, depending on. So if I have such an endomorphism, the trace of it will give me a section of omega 1. And so the trace of the exterior powers of this morphism will give me sections of this exterior power. And so fiber-wise, it just takes the characteristic polynomial of this endomorphism of this thing. And the key observations is that the fiber of this morphism are actually easy to understand. So the insight is that what is the fibers. And to explain this, let me do a so usually when I try to explain this, it gets a bit yes, to explain it, before I explain it, let me explain the linear algebra thing in an algebraic geometrist way. So let's do the fiber-wise thing first. So suppose you have a vector space with an endomorphism. So if you have an n-dimensional vector space with an endomorphism, then you see, then you know that this is the same as to equip V with a module under the polynomial ring. That's you just so if you give yourself a module structure by saying that you apply T, means just that you apply phi to T. So in this module structure, by Cayley-Hamilton theorem, you know that this every morphism satisfies its characteristic polynomial, so it factors through the characteristic polynomial. So it's a module, so V is both a K adjoint T, module the characteristic polynomial. So let's call this chi of phi module. Okay, this you probably know. And so now as an algebraic geometer, you say, well, okay, a K joint T module. The K joint T is the functions on the affine plane. So a K joint T module is a sheaf on the affine line. So this K joint T module is the same. V is a sheaf on the affine line. and that it's a module under this says that the supported on this subset. Yeah, so that's a zero-dimensional subscheme. And under this corresponding, so of course you see that that's why Jordan decomposition and modules under principal domains are so closely related, and so the eigenvalues of phi, they correspond to the support points in the support of your sheaf F, right? So far, so good, right? This looks like doing transforming simple linear algebra into complicated algebraic geometry. But what's good about this, I mean, at least what I like about this description, is that if you think of a family of operators, then and you can go back and so maybe I should say, sorry, eigenvalues were the points, and what was this V? So this V was just the global sections of your sheaf. Right. So why is this a good perspective? For me, this is nice because it doesn't actually matter that we were working over a field here. So if I would have a family of linear operators depending on some parameters, I could do the same construction and I would get a sheaf on the A1 times the base of my parameters. And so you can sort of get a feeling for how can the Jordan decomposition of my operator change? How complicated is this question? And well, it's as complicated as how you have sheaves of length n on affine line, which is for me more geometrically graspable. And so that's what we can do here. So we can globalize this. We globalize to this thing. Now, so how did I want to write it down? So what's now I have this vector bundle with this twisted section. So now let me turn it around again, because so that's just the tangent sheaf of my curve. So so if I do this, then this is the same as to say that E is a module for, so E was an OC module before, and now it became an OC module where I join a variable that comes from this tangent sheaf. So this is my analog of the polynomial ring. And if you want to do fancy so algebraic geometry language, then you say that this is the symmetric algebra of this sheaf, but it's just a polynomial ring and the variables that come from T. And this is the same as a sheaf on the, so these are just the functions on the cotangent sheaf. And what it's supported on, well, the spec of this algebra divided by the characteristic polynomial of phi. So this is usually called the, well, I should give this characteristic polynomial a name, but this will be, because it's a point in the Fitchin base, it will be usually called A. And so this is called CA, which is a closed subscheme of this cotangent bundle. And fiber-wise, like in this case, this is a degree n map. And this is what's called the spectral curve. Yeah, and there's a way to go back. If you give me a sheaf on the spectral curve, such that what we know we need to have here, so we wanted that V was a vector space of dimension n, so I have to take global sections have to be n-dimensional. So I have to take something on the spectral curve such that the push forward is a sheaf of rank n. It will give me such a Higgs bundle. So that's what goes under the name BNR correspondence. And maybe Schaub also needs to get some mention that there's actually a correspondence between these Higgs bundles on C where the characteristic polynomial is A. This is an equivalent to F, an OC torsion-free on this spectral curve that is of that has of, well, I would like to say rank 1, where this rank has to, I mean, we see how we have to interpret the rank. So the rank 1 thing just means that the dimension as a module under the function field of my curve of this, if I restrict it to this fiber over the function field, then this should be the same as same dimension as this. And why does it have these two names? So this is, so we just proved this because it was just taking this description and saying it works in families. No, this is the point I want to get to in a second. This is just like here, right? I mean, this thing will be reduced if and only if my polynomial has distinct eigenvalues. So when will this spectral curve be reduced? Well, it will be reduced if the generic point, it's reduced over the generic point. So if this phi generically has distinct eigenvalues, you get a reduced spectral curve. But I mean, phi, for example, could be the zero map. So if phi is the zero map, well, if phi is the zero map, what's my characteristic polynomial? It's just t to the n. What does it mean for the spectral curve? Then it will be nth thickening of the zero section of this tangent bundle. Right? Just if you take the zero morphism there, or a nilpotent endomorphism here, you will get kt adjoint divided by t to the n, which is an length n subscheme of A1 supported purely at 0. Yeah, and so that's actually what will happen to this thing. And so this is what I want to discuss next a little bit about this geometry. What geometry do we get for the spectral curve? And so if you put stability here, you still get an equivalence if you put the right notion of stability here. And that's probably why these names get attached, or semi-stable. They can do both. And one thing that I also wanted to notice is that you could just as well, I mean, it doesn't, for this thing, it didn't matter at all that we had the canonical sheaf here. We could take any line bundle, and then, so we could replace take any line bundle omega of d instead of d omega, and then we would get these spectral curves sitting in, well, the total space. So the geometric realization of the dual of this. Right? Sorry, no. Sorry, there's too much confusion. I mean, sorry. So it's always because that's the reason why we put the omega on the right-hand side, so that it gets on this geometric realization on the of this sheaf. The functions are on the others. So we always get spectral curves that are of degree n, but they can be bad, as just you said. So why do I say this? Because this allows you to picture some examples. Maybe let's picture some examples. So what's the geometry of these spectral curves, and why is this actually a nice thing? Good. So let's take some examples. Yeah, so yes, maybe I do. Maybe I do it like this. So what does this mean? So you get, so generically, so what will be the spectral curve be? So you get it's a 2-to-1 cover. And so what are the bad examples that you can think of? So for example, inside here, you could have so inside of A, okay, so the first thing to notice is that this factor is kind of the boring factor. Why is this the boring factor? I mean, that's so if I have one spectral curve, I can just translate it by a section of T star. And I will just shift it around, so the geometry of the fiber will not at all change. So this corresponds to changing this constant coefficient of my characteristic polynomial. So this is sort of the boring coefficient I'm not really care about. What I care about is this thing, and this tells me that I will get, generically, I will get a curve over P1 that's ramified at 4 points. So generically, I'll get an elliptic curve. So generically, get elliptic curve. So the general fiber will be some, well, will be some torus. Now, what can happen? So as you just said, I could have that generically, my characteristic polynomial, for example, it could be split as a product globally. It could be the product of two things. So CA could also be the union of, so that A could be the product A1 times A2. What does this mean? It's just the product of two sections of O of 2. So this would break up in CA1 times CA2. Now two sections, here I would just have two sections of my, so this is two sections of O of 2. So it's just two P1s meeting at, well, the intersection will meet at 2 points. Because I have two sections of O of 2, so that thing will be generically at 2 points. And then you, as you said, the worst thing that you could have is if you take twice the same section, you will get a non-reduced curve. And of course, many other things can happen. So in between, you could require singularities and so on. So that's your picture. So if you look at this picture, you will find some favorable and some less favorable properties. So let's list them. Yes. So there's one thing that so there's something that's always confusing for me. It's the numbering of the coefficients of my characteristic polynomial. So if I take an right, if you let me think. Right. So if I give you an endomorphism of a vector space, one thing that I could do is just add a multiple of the identity to it. Then this will just shift the eigenvalues around. So this picture of the subsheaf of A1 just gets shifted around. And this is the same that I can do here. So if you give me a section of omega, I can just add to phi the identity times the section, and it will just shift my characteristic polynomial around. And so this is sort of captured by this thing. And of course, you have to, now it depends on which symmetric polynomials you take and so on, but that's this factor that's responsible for this. So you could sort of fix it by requiring that your trace of your operator is 0, and then you would have rigidified this. And then you over. So that's why I put the 0 section, reduced 0, non-reduced 0 section. So what is the properties? So the positive things are to notice all T of A are connected. Well, this was because we started with a positive line bundle. And if you would start with an elliptic, otherwise you could. That's nice. And for generic A, the CA is smooth. So this implies for me that I can describe this inverse image of A in this case. Well, it will be rank 1 torsion-free sheaves on an integral, on a smooth curve. So this will just be line bundles. And now you have to put some degree here. And you can. Yes, yes, yes. So this is, I'm in Italy, so this is a sort of, yes, Bettini's theorem, I guess. What people told me. Yes. So that the generic section of this, that these sections are connected is, it follows because this is an ample bundle. I mean, you see that, of course, if you take an elliptic curve and take just the trivial bundle over it, you could just take 2 disjoint sections. But the positivity of the bundle declares that this is impossible. And so here I put a D prime because, of course, because you know that so if you would number the components of the Picard by the Euler characteristic, it would be the Euler characteristic of your Higgs bundle. And I don't want to mess with these factors of G. So I just write it's some degree that you can compute out of the D from the thing. So this is nice. But there's a minus point. Maybe there comes a plus point, another plus point. But CA can have several components. Or be non-reduced. And now the problem starts if you look at, even if you just look at line bundles on this doubled curve, I mean, if you fix their Euler characteristics, this tells you something about the sum of the degrees of the restriction to the 2 curves. but it doesn't tell you anything about what these degrees on the two curves are. So under this Hitchin morphism, so this says that h minus 1 of A, so without stability, h minus 1 of T would contain would contain line bundles on this non-reduced curve of total degree E prime, and this has infinitely many. So this is actually turns out to be open in this case. So it's integral, then that's true. Infinitely many irreducible components. Infinitely many isomorphic irreducible components. So this tells you why without working with stability, this vibration, which looks, this map H that I erased from the set of all Higgs bundles to this affine space has enormously large fibers. So that's bad. So this is why we need stability. And this is actually, I mean, if I look back to this first lecture that I told you about, in the first lecture, I told you that Schiffman and later Hongzhe-Yu managed to count the number of points of the space of semi-stable Higgs bundles over a finite field. And the key problem for this thing is that, well, counting all Higgs bundles without stability would be something that we actually know how to do. The problem is just that because of this phenomenon, the number you get is infinite. And it's infinite in a bad way. It's actually, you write down a sum where you sum over the same term over and over again. And so you need to truncate this summation. And well, that's problem to do this in a way that you can actually control what's happening. And so they found two different ways of doing this, one using trace formula methods and the other one a more geometric one. And the same happens here. So same problem, similar problem. It's a similar problem here, sort of, if you fix the Jordan type, then many things can happen. Of phi. Okay, so this is the bad news. Maybe I should add something more pleasant. So if A is if CA is integral, then this torsion-free sheaves, then so the modulus surveys of ranked 1 torsion-free sheaves on CA is known as the compactified Jacobian. And this has been studied a lot, and we know a lot about this. So in our toy example here, I mean, if you look at this pinched P1, you might know that the Picard group of this thing is the multiplicative group, because you fix the degree of the line bundle on the normalization. You can pull back to the normalization. It's P1, so a line bundle on this thing is the line bundle on P1, where you identify 2 of the fibers. And for this, you have a GM choice. And now the funny thing is that, so this is a GM, so it's a bit unfortunate that this is not compact, but you can compactify by adding 1 point. As you see, you could just take the curve again. And this is actually what you can do. So if you take these GM, you could specify them by just saying, well, you take O of some point on your curve. And if you take the nodal point, you get something that's not locally free, but only torsion free. So your compactified Jacobian will look like this curve again. So it's a singular thing, but it's not too bad. Okay, so this is the good and the bad news. Let me check whether I forgot something. Right. So the theorem that I would like to state is that this description, sorry, this was stupid to erase it, but this description tells you one thing, that this relation to the Jacobian is actually a nice one, because you see, if you take a torsion-free sheaf on any curve, and you have a line, happen to have a line bundle on this curve of degree 0, you can just tensor it and you will get a new torsion-free sheaf. So the Jacobian of your spectral curve will always act on this fiber. And this actually is a good thing. So the theorem, well, due to many people, and I don't list them, is the following, that the morphism H, when you restrict to the semi-stable part, so I'm sorry, I cannot decide whether I want to call it M Dolbeau or Higgs, and D semi-stable. A is proper, projective even. So once you pass to the moduli spaces, and carries an action of the Picard group of the universal spectral curve over A. The fiber-wise action. What did I do? There's an action of the relative Picard of line bundles on the spectral, the family of spectral curves. Over the Hitchin base. So this is in the line of things that, I mean, you should always sort of try to observe all symmetries that your situation has, and that is sort of the first bit of the symmetries that we found. Okay. Okay. Questions so far? Or is this? So that's a kind of a very beautiful vibration. And there are some two remarks that I wanted to make on this. There are several natural compactifications that you can see from this picture. I mean, from this picture, you already see that this space will not be compact because it's projected over some affine, and this is actually a flat morphism. It's surjective. So what are they? So there's two things that you can do, and both of them are useful. The first thing is to, well, we can think of, we saw that Higgs bundles at E comma phi, they are the same as certain sheaves F on the cotangent space. So a torsion, sheaf supported on a one-dimensional subvariety of the cotangent space. And so you could just projectivize the cotangent space. I don't know how to write this. So you just add a copy of a one-dimensional. So is this a reasonable way to projectivize this line bundle? Just add a section at infinity. So you take the projective bundle of T star plus O. So which is a surface. And so you can look at this Higgs and be semi-stable to sit inside some moduli of sheaves on the projective surface. That is the projective closure of your bundle. And these have been studied, and if you remember from last lecture, so at some point I needed to have a compactification of this that I can still express as a moduli of sheaves, and that's the one that Markman uses. And there's a second natural compactification, is that this Higgs to A carries a C star action that is contracting to the zero fiber, which is proper because this morphism is projective. And so you can always compactify such a thing by saying that, well, A, you can embed into the projective space that you take, well, you take A, take an extra copy of C and divide out by the diagonal C star action. And so here you have to remove the zero space. So this will be a weighted projective space. So weighted, because if you see the C star action on Higgs bundles was taking your section phi to lambda times phi. So on the characteristic polynomial on the coefficients, you will act as powers of I. And so on this summons that I wrote down, the first summand you will act with weight 1, and on the second with weight 2. So this is a weighted projective space. Over this, you have your Higgs. And you can do the same thing to this Higgs. So you can take, what do? You just complete the action of C star. And now what do you have to remove here? I think you have to remove just the pre-image of 0 times 0, divide by the C star action. And this will be projective again. So what you just did here, sort of you completed your affine space by gluing in the projectivization of it on the boundary. And the same you can do for this family of Higgs bundles. You can just glue in the projectivization of this. So this is sometimes Higgs bar. And that's also useful. We'll see, hopefully, in a moment why. Yes. Yeah. Yes. So you. Yes. No, it's a now okay. But you know that okay. So you have to choose. I mean, you have to see which semi-stability condition you want to take here. So for me, I mean, if I look at semi-stability, that for me semi-stability comes from taking the line bundle on the moduli problem that comes from determinant of cohomology of your sheaf, and this makes sense on the other side. And so you just have to check how to extend it correctly. So you find a line bundle here that gives you a semi-stability condition that restricts to the correct one here. But yeah, and of course, I mean, you may know that stability conditions on the surface, they depend on the choice of some divisors. And there's, of course, the question is here, which multiple of the section of infinity do you use? You have to compute. More questions? Yes. Yeah, so you see, your spectral curves, your family of spectral curves. So what happens to the spectral curve when you use the C star action? Well, I think of my spectral curves to be these eigenvalues distributed in A1. And now if I multiply, I just scale them out. But the compactified Jacobian, they will not change. So if you put yourself on some point that's not zero on this thing, you find a compactified Jacobian in the fiber, but it doesn't actually change when you move along the C star action. And so at the point of the projectivization of the image, you just keep this compactified Jacobian. Yeah. There is, yes, more questions? There is one stupid observation about the linear algebra part of this that I forgot to make, that I wanted to make in case you want to look at one of these P equals W articles. That is, I mean, from point of view of sheaves, if you look at this, where did I put it? If you look at this as a sheaf on the cotangent space, it's not a very nice sheaf because it's not locally free. But from point of view of homological algebra, it's not too bad, because you know that there is a canonical length 2 resolution of it by vector bundles. And this comes just from this writing your vector space V as the support of a sheaf. So you have a canonical surjection from V, from the locally free sheaf that has global sections. Also O of A1 tensor V to it. And the kernel is again O of A1 tensor V. And the resolution that you get is just you get K joint T tensor V to K joint T tensor V, and you multiply by T minus 5. That's sort of, if you're going to compute a fitting ideal of this thing, that's what you do. And this, again, you can write out for these things. So these torsion-free sheaves have a natural length 2 resolution by vector bundles, and you can again get it from just trying to write down a locally free resolution of your module V over the polynomial ring. And that's something you just can do. Okay, sorry, it was an aside. I should have written it down. Maybe I should. And these are locally free. And so this implies that this F on T star D has resolution by vector bundles. These are rank. Maybe it's helpful to know. So this is useful in case you want to compute Chern classes of this F in terms of the surface. Then you want to have a resolution by vector bundles, and there's a natural one that is given to you from the start. Good. Okay, any more questions? Because the next thing I have to do is to tell you what this P filtration actually is. So I was trying to push this. On the cohomology, this Higgs moduli space. And there's two answers to this. There's two descriptions. A global one. And the second one is a sheaf theoretic one. And the sheaf theoretic one was first. The global one is now easier to write down. So, so the global one is easier to write down, but incomprehensible to me unless I know the sheaf theoretic one. So, but maybe let's at least give you the global one. So we have this Higgs moduli space. And we have this nice compactification of it. That sits over A, sits over A bar. And well, so this, and this is Q smooth. If N and D are coprime. So this, yeah, that's the second one that I gave the name H bar. So it's the one compactification that is compatible with the Hitchin morphism. How far are they different? It's a good question. And I don't know a good answer to it, but I should know, and I just don't know. I have to think. I think they are related, but I don't quite know. But this is the one for which, I mean, this is actually one of the points where, okay, that I'm actually struggling with. But okay, so that's for another, right? So how to write down this? So you know that if you take an ample, so these are all projective. This map is not smooth. That's the key trouble. They're all projective and smooth, but H is not. That's our trouble. I mean, we saw the fibers of H, there were these compactified Jacobians, which are singular. So good. So what we would know is that if we take an ample class, now I have to ample class on Higgs bar, then it satisfies the Hard-Lefschetz theorem. So if I take C1 of LA bar and pull it back by H, does not. Why should it, right? It doesn't know anything about the things of the fibers. But the Cataldo Migliorini noticed that the perverse filtration sort of is exactly takes count of this. So they proved that this nilpotent operator on the cohomology of the space induces a filtration. So any nilpotent operator on a vector space induces a filtration that corresponds to the Lefschetz decomposition of this. It gives you a filtration of this vector space such that the operator then satisfies hard Lefschetz with respect to this filtration, And this is the P filtration. And so, because we know that this cohomology of this thing is pure, we know the image of the cohomology of this proper thing inside here is everything. So this is surjective. And so that's the P filtration that we get here. So that's the easy way to say it. That's, on the other hand, for me, it's the completely incomprehensible way to see why any of like this should be true. Where does this come from? And I have 5 minutes left. And maybe I try to say something in 5 minutes. And then you can complain, and then you can ask me to say some more minutes tomorrow. So that's the one that I can write down in 5 minutes. And so but it's not very illuminating for me. So what's the sheaf theoretic one? The sheaf version is the following one. So that's it says it comes from the decomposition theorem. So Beilinson, Bernstein, Deligny, Gaba. So the good thing is, so originally Gaba refused to sign the article, but in the new edition that the SMF put out, he agreed finally to become an author. So now this theorem should get the right name. Again, so this is this decomposition theorem. So what does it tell you? So the starting point is maybe the following. So it's the following. So if you have x to y map pi, where pi is smooth projective, and maybe we assume x and y projective. No, let's for the moment let's do x y projective. It doesn't really matter. Then you can look at then you know if you take the cohomology of the fibers, they are locally constant. On Y, plus they carry a Hodge structure. That's the Hodge structure coming from the fibers, which are smooth projective varieties, so it's a pure Hodge structure. And from this, you can deduce that this R pi lower star of Q, that the complex actually decomposes. So if you want to compute the Leray-Birkfeld sequence of this, it degenerates. So this fails if the map is not smooth and you're stuck. And this decomposition theorem tells you that a similar result is true for a projective map, that you can again decompose this complex into simple terms, but they are complexes. So, and plus the Ri I lower star Q as sheaves satisfies relative hard Lefschetz and Poincare duality. Saying if you take a cup product with a relatively ample class, it will shift these complexes by 2, and you get these relative isomorphisms, and Poincare duality tells you that the lower one is dual to the other. And decomposition theorem tells you that there's similar thing happens tells you that, again, this RP lower star Q is a direct sum of so if X is smooth and it's proper and made projective thing, so that this relative Lefschetz is makes sense. Then you can again of projective flat, say projective of relative dimension D, say, then you can again decompose it into 2D summons, which are so I have to give me a second. Yes. So I should put this map from X to A, so that this is the A of our and then you have to shift it back. You can forget about this. I will explain these shifts in a moment. I hope maybe on Friday. I guess that's now right. So it has direct sum decomposition where these are called perverse sheaves. And they are complexes, but they have a kind of a relatively simple structure. And sort of this P filtration, Pi of H star is the image of this direct sum from Pk of this is the I equals to 0 of K of this decomposition. So again, so I'm kind of cheating a little bit. So what I'm cheating is that this direct sum decomposition is not canonical, but the filtration is. And so this inside of the cohomology of X. And so the P equals W conjecture. So this conjecture was that I was talking about is that this Pk of H star is the weight filtration on this Mbeti side. So Mirko is in the audience, so he will probably shout now if I messed up the indices. I will talk about these indices hopefully on Friday. I think it doesn't make sense right now, but I think they are right. Okay, so it's this for now. This sounds magical, but there's a reasonable explanation. And I will try.
Thank you. Are there any questions?
Yes, yes, yes. So yes. So that's what I want. So yes. So that's why I wanted to put flat. Yes. Which the Hitchin morphism is, and I forgot to say.
So when you have this class, the H bar star C1 of L delta bar, when you transport it to Betty, what is the interpretation of that class?
I mean, this class,
yes,
this class has the trouble that if you restrict it to A, it becomes trivial.
I understand, but I pull it back, then I see it on X. This lives in the cohomology.
No, but I mean, if I take this class, I pull it back here, it becomes trivial. So if I pull it back to Higgs, it's still trivial. If you transport it to the Betty side, it's still trivial.
But then this is very strange. I mean,
I told you it's very strange. Yeah, so that's right. So that's why I find this description that is convenient to write down is very confusing from the side of the filtration. So this description doesn't make any sense on the Betty side right now.
No, there is something I don't understand. I mean, this class lives in the cohomology of the compactification of Higgs.
Yes.
And now you're saying that this identifies with the cohomology of Higgs. So
No. I say that this cohomology surjects onto this cohomology because this cohomology is pure.
yes.
So I can take the filtration here and pull it back to filtration here.
Yes. No,
Right.
I understand that, but still it's very confusing.
Yeah, yes, I pretty much share your confusion. I mean, that's a way to write down this filtration, and it's for the moment completely unclear what this means in terms of this filtration only because it was just constructed using a compactification.
Yeah, but then maybe another question is then what is the kernel of that map from the cohomology of X bar to cohomology of X?
This is something you can actually compute because
this is where this class is living.
Yes. So maybe this is the good question. So for this, I think we should just go as Geordie said. We should look at equivariant cohomology because then, so you see what's this class? So this Chern class of this weighted projective space. The weighted projective space is a truncated polynomial algebra, but it actually comes from taking the equivariant cohomology of this completion. So if you look at the equivariant cohomology of this completion, you will just get that everything is a polynomial ring over the cohomology of the zero fiber, which is the cohomology of the same thing. And then by Gaussian sequence, you can compute what this kernel is. So there's a shift. And so I think this way you can actually see what the kernel is and where this class lives, and you see that there's a little bit of funny shift in this from the C direction.
So very roughly so another way of phrasing the co-kernel of the Gaussian or whatever would be as you take the complement of like nilpotent Higgs fields or something, no? Or
yes, so if you do equivariantly, then yes, right? Because you say that can you say the question again?
like roughly speaking, in Higgs bar.
Yes.
So another way of thinking about what the complement is it's like I take away the zero fiber and then I mod out by C star.
Yes. Yes. Yes, and this contracts to this thing. So right, so this is a way to think about it. I like to, yes.
And maybe just another comment. I mean, I absolutely adore the work of Nicola Migliorini, but I think that this thing that the perverse filtration is like the kind of Jacobson-Morozov filtration associated to a pullback of an ample class from the base is, you know, basically already in Deligne and BBD.
Yes, but they don't state. I mean, they. I mean, yeah, they don't write down the statement, and so they get the fame. I agree. That sort of if you manage to read this asterisk and digest what's written on hard left sheds in the end, then yes, you can get this out. But this is a posteriori, and I think, I mean, there's still this non-degeneracy. I mean, this positivity of the intersection forms on the quotients. That's something that's not really in BBE because they don't talk about. I mean, they do L-adic homology, so they cannot even formulate this in some sense.
Okay, but when you complete by Jacobson-Morozov,
yes,
maybe you can manage not completing from the base. The other operators.
Hmm?
I
yes.
mean, you have this diagonal operator, but you complete it. You have this nilpotent operator, but then you complete it. But you can manage so that it does not come from the base, the SL2 triplet.
Yes.
And then this survives.
Yes. Yes, I guess, yes. This is exactly what you, yes. Yes.
Other questions? If not, let's thank Jochen again.
So let me start with another quick announcement. So we decided to follow a suggestion which came from Geordie right before lunch. So we prepared this beautiful handmade question box. So everybody is welcome to drop a question in this box, and the speakers will be happy to stay for 1 hour after the last lecture and try to answer your questions. So you can drop the question during the break. Okay. So yeah, thanks.
Thank you. So, yeah.
Oh, go ahead.
No, please. No, please. I want you to introduce me.
Yeah. So it's my great pleasure to introduce Javier for his last talk.
Thank you very much for the introduction. Yeah, so before I get started, are there any questions that you feel like asking publicly now? Well, you can use the box. So recall. So one of the things I did yesterday was to sketch a construction of a Norris category of motives. So this is a category of motives for subfields of the complex numbers that I denoted MK. And well, there were two parts of the construction. The first one was quite formal, and it gave rise to an abelian category. And then there was a second part where I explained that this is actually endowed with a tensor product. And with respect to this tensor product, it is a Tanakian category, which concretely for us means that it is the category of representations of some pro-algebraic group over Q, which is called the motivic Galois group. This is a pro-algebraic group over Q. And I try to explain some of the geometric inputs of this Tanakian structure. But there's one I didn't mention, so I want to start with this small complement, which is duality. Okay, so one of the important things you need to do to prove that something is a Tanakian category is that objects have duals with respect to a tensor product. And so this you can imagine is some form of Poincare duality, except that we are working with all kind of varieties, so not necessarily smooth projective. So you need to be a bit careful about what Poincare duality means. And so you remember when I constructed the tensor product, the important step was to show that you don't need all varieties and all subvarieties to construct the category. You can restrict to the subquiver where you only consider affine varieties, and more importantly, this property that the cohomology of the pair is concentrated in a single degree. So to prove that there is a duality, you need another presentation of the category. So the first step is to use resolution of singularities. To show that MK is also generated by so objects X, Y, and I as usual, but now X is smooth and Y is a simple normal cosine divisor. Okay. And then it is enough to show that objects of this shape have duals. Okay. So then the form of Poincare duality you use is the following. So let's take X bar, which, well, as you can imagine, is smooth projective. And assume you are given two simple normal cosine divisors inside. So that's the union is also a simple normal cosine divisor. So all these three things are simple normal cosine divisors. And then you can do the following thing. You can consider the cohomology of X bar minus D1. Okay, so this is this smooth open if D1 is not empty variety. And resolution of singularities tells you that you can obtain any smooth variety in this way. And then do cohomology to D2. Okay, well, you just need to add some decoration because D2 usually will intersect D1. So the thing to consider here is D2 minus the intersection with D1. And we want a dual for this cohomology group. And then this thing will be, so maybe let's try to guess what should we put here. So imagine D2 is empty. So here what you get is the cohomology of the complement of D. And you know that from Poincare duality that what you are supposed to pair this cohomology with is compactly supported cohomology. And compactly supported cohomology, one way to think about it is as relative cohomology of the compactification relative to the normal crossing divisor at the boundary. So this suggests that this D1 is going to pass to the other side in the duality. And then this is what happens in general. So if this is a variety of dimension D, then you have 2D minus N, and then you change the roles of D1 and D2. Okay, so the statement is that there is an intersection pairing between these two things that takes values in Q minus D, and it is non-degenerate. Sorry. D1 minus the intersection with D2. Yeah, thank you. Okay. So this is the geometric ingredient going on in the proof of duality. And I strongly suggest that you think about this as an exercise. And so let me give you the necessary information, which is that at some point I used that singular cohomology was also sheaf cohomology. So you can realize it as the cohomology of the constant sheaf. And so what about relative cohomology? So for relative cohomology, what you need to do is consider the complement of of y in x. So let me call the inclusion beta. And then relative cohomology, so cohomology of x relative to beta. This is the sheaf cohomology, maybe Betty cohomology. So you can compute this as sheaf cohomology on x of what? Of the extension by 0 on, so this is an open immersion, of the extension by 0 of the constant sheaf here. Constant sheaf is the same thing as the pullback of the constant sheaf. Okay. So if you, what you need to do is to interpret both sides as a sheaf cohomology group, and then try to compare the sheaves using the local structure of a normal crossing divisor. So this is false if you don't assume that your thing is a simple normal crossing divisor. Okay, so this is a complement I wanted to make. And yeah, so let me now focus a bit more on the motivic Galois group. So this is a huge group to work with. So in practice, what you usually do is you consider a motive. So M is a motive. So for example, you can think that it is HNXY. And then instead of taking the whole category, you consider the Tanakian subcategory generated by M. Okay. So this is telling you that a motive is a representation of this group. Okay, this pro-algebraic group. This category will also be the representation of something, GM. So GM is a quotient of this motivic Galois group, and it is the finite dimensional quotient through which the huge group acts on this object. Okay, so you will get a GM inside GLN, GL of, and maybe let me write, well, let me just do it for this, not to introduce more notation. So you get a subgroup inside the linear automorphisms of singular cohomology. Okay, and this was constructed using the formalism of Quiver representations and its tensor product and so on. But this should not obscure the very elementary nature of what we are doing, which is you look at linear automorphisms of relative singular cohomology, and you consider those. So this will be the subgroup of those which commute with all the maps that you have decided that are relevant for this problem. So in our case, these are the maps coming from geometry, and coming from geometry means so induced by morphisms of pairs or induced by a boundary in a long exact sequence of triples. Okay, so if you ask that it commutes with everything, you will get the trivial group. If you ask it doesn't commute with nothing, so you will get the whole thing. So this is the construction of the category. We are putting the minimal quantity of morphisms for the comparison and the period integral to be injective, to have a chance to be injective, and this is the group that commutes with all these maps. So the next exercise you should do is to consider M as H1 of an elliptic curve. Okay, I'm just, yes? yeah, the thing that really makes sense is you consider all motifs simultaneously, so you have one group for each, and it will commute with all maps between the motifs. You know, if you have a map that goes from X to X prime, so you will get a pullback map here. And then when you consider the group of this other one, you want that it something comes from here, so it commutes with the. Okay, so you already know the answer, so I'm just repeating from Bruno's course. So in this particular case, you get a subgroup of GL2, okay, because the commodity is two-dimensional, and then the typical way of doing things in this Tanakian business is you try to collect as many informations as you can about the group, and then use some representation theory to conclude that there is only one group satisfying all these constraints. So what are some of these informations in this case? So we know that this is a reductive subgroup. So because reductive in the Tanakian walls corresponds to semi-simple, and this is a pure motif. So if you have something, the Hodge structure is pure, for example, you will get reductive groups. You also know that if you consider the determinant of this group, so the determinant is a subgroup of GL1, and it is equal to GL1. Okay, so this excludes, for example, the case of SL2. And this is because the determinant of the motivic Galois group is the motivic Galois group of the determinant. So you need to compute the determinant of H1 of E. So this means the second wedge power. And this is, well, in this particular case, you know, well, this is topologically, for example, is a torus. So you know the cohomology algebra of a torus, and you know that it is a stereo algebra on H1. So it is actually the H2 of the elliptic curve, and H2 of a smooth projective curve is always equal to Q of -1. Okay, it's actually always the same as H2 of P1. And then this I computed yesterday. The motivic Galois group of this one is GL1. Okay. The manifestation of this thing I'm saying is that if you write the period matrix of an elliptic curve in some basis, and you compute the determinant by the exercise I gave yesterday, this determinant will be essentially and literally, if you choose the base properly, equal to 2 pi I. Okay. And then this 2 pi I here is the period of the determinant Q of -1. Okay, so you know these two things, and then you know that the endomorphisms of M. This is also a very special property of abelian varieties, that the endomorphisms of H1 of the elliptic curve all come from endomorphisms of the elliptic curve. This is actually the same thing as the endomorphisms of E tensor Q. And there are two possibilities. So it is Q. In this case, you see E has no complex multiplication. And it is an imaginary quadratic field. And in that case, you say E has complex multiplication. Okay, so this says, for example, that the commutator of so you know this induces maps on H1, and the motivic Galois should be containing the commutator of those maps. And well, you put all this information together, and then you get that. So in the first case, the group will be GL2. And in the second case, it will be, well, a two-dimensional torus. So you get this easily. And if you are a bit more precise, you get that it is exactly the torus that was appearing in Bruno's talk. Yes. this thing here. Thank you. I'm computing the endomorphisms, because each time you have an endomorphism that acts non-trivially in cohomology, so this will produce a constraint for the group. Okay, so now I can state, yes. I think you, I don't know if you can do this without Hodge theory. I'm not sure. I would say no. Really, you need Hodge theory here. Well, you really need to use something, because as you could try to argue that you know, this object is simple, and okay, if you know what are motives of dimension 1, then you would know that this is simple. But to know what are motives of dimension 1, you need Hodge theory. So I should think about it, but I don't think you can get around without any Hodge theory. Yes. Well, it will mean, so you need to use several things. So first one is that if you have a Tanakian category which is semi-simple, then the groups are reductive. So this is one thing, which is not hard to see. Well, it might be the definition if you define reductive groups that way, but well, there are other ways to see that. And then you, for example, you can, the quickest way to do that would be to prove that this group is the Manfortet group. Okay, and then you use that information. But you don't need to do that. This is a bit too much. You can, but still you use some Hodge theory to prove that it is reductive. Okay, so yes, please. A smooth projective. I think that's true also. If I can assume projective here. When I was preparing the lecture not so long ago, first I wanted to put projective, but then I think I'm not 100% sure. I think it works, but you need to check something. Okay. Is this what I write in my book? Yes. And we take it projective, smooth projective. Okay, well, if it's in my book, it should be true, right? Thank you. Yes. Why is this true? This is a form of Torelli's theorem, for example. Yeah, this is one way to see it. If you are okay to work with analytic methods, you take your elliptic curve, you realize it's at a quotient by a lattice, and then yeah, and then the cohomology will be the homology will be the lattice, and every endomorphism leads to the universal cover, and you really see it. And it's also a property. Yeah, well, it's more generally a property of abelian varieties, well, that I guess you see in the same way. Okay, so yeah. I state again Grothendieck's period conjecture because I'm going to try to relate it to a Kontsevich-Zagier conjecture. So it says that if you take so K inside the Q bar, so it's reasonable to talk about periods. And then it says that the transcendence degree of the field generated by the periods of a motive is equal to the dimension of this motivic Galois group. Okay. And in this conjectural equality, this inequality is true. Okay. And it is, well, everything depends on the way you define the group here. If you do it with this formalism, this is essentially a trivial consequence of the formalism. If you put here the Manford-Tate group, then it's another story. So this is, if you put the Manford-Tate group, this is known to be true for abelian varieties, but well, it's a theorem, and it is not known to be true in general. Okay. Okay. So in this case, so you compute the period matrix of an elliptic curve, you will get 4 numbers. The conjecture says that if for most elliptic curves, these numbers are algebraically independent, and if your elliptic curve has complex multiplication, then there are 2 of them which are algebraically independent. You already know a way to exclude one of them, because you know in this case that tau, which is the quotient of 2 periods of the holomorphic differentials, you know that this is algebraic. Okay, so this gives one relation between 2 periods, and there is another one. So the upper bound is not hard. And in that case, we know that this is true. So there are 2 cases where the conjecture is known. So 2 cases. If you consider H1 of GM, so here you get the group GL1, which has dimension 1. And this is the field generated by 2 pi I. So the statement is that 2 pi I is a transcendental number. So this is due to Lindemann. Not in this form, and if M is H1 of an elliptic curve with complex multiplication, then the 2 numbers you get after you remove relations are known to be algebraically independent, and this is a theorem of Chudnovsky that, to my knowledge, no one has properly understood or tried to reprove or generalize or whatever. Okay. So, yeah, so I want to explain quickly how this is related to the point of view of Kontsevich-Zagier. And for this, let me go back to MK. So MK is, I said, is a Tanakayan category. It is defined as Q vector spaces plus the action of these endomorphisms of the quiver. And if you forget the endomorphisms, then you just get a vector space, which is the Betti cohomology. And this is the functor you take. Okay, so this functor, now I'm going to call it omega Betti. So omega is the usual name for a fiber factor, and Betti because it's Betti cohomology. So this is the one that goes into the construction of the category. And then you can construct another one, which I'm going to call omega de Rham, which is the de Rham realization. And this is a bit involved if you work with a whole quiver, because then you need to know what is relative cohomology of singular varieties. And well, you can do that. So there's a construction. But if you work with the quiver where things are smooth and normal crossing divisors, you will just send X, Y, and I to H and the RAM X, Y, I. Okay, and then this is the construction I explained maybe, I don't know, 2 days ago. So, okay, and then general Tanakian thing you can do when you have two fiber functors is to look at all tensor isomorphisms between them. Yep. Well, the image to have in mind is always the image of topology. So if you consider local systems, so local systems is form a Tanakian category. So you can take products of local systems. And if you choose a point of your space, then you have a fiber functor, which is taking the fiber at this point, okay? And then you get the fundamental group you get is related to the topological fundamental group at this point. But you can choose another point and then consider paths between them, okay? So the group here will be something like an algebraic version of the fundamental group of your space, and this thing here is something like the space of paths from one point to another. And as you know, if you have a path from one point to another, then you can compose with an element of the fundamental group, and then you get another path. Okay, so it's the same thing. Here, the motivic Galois group is defined as the automorphisms of this functor, and this means that this is a torsor under the motivic Galois group. So torsor includes in particular the fact that this is not empty. And you know that it is not empty because you know a point of this space over the complex number. So you know a complex point, which is the comparison isomorphism between the ramp cohomology and Betti cohomology. Okay, it's a space defined over Q, so it has a complex point. It also has a Q bar point. So there exists an isomorphism between these fiber functors, which is defined over Q bar, and it's compatible with tensor products and everything. But who knows what this is? And you can prove, so this is something, I wouldn't call it an exercise, but something to think about. Over Q bar. No, I mean, the space is defined, well, it's defined over K. Yeah. I mean, if I want to do things properly, so either K is equal to Q or here I need to tensor by K. Thank you. So something to think about is that this has no rational point. Not it's hard to think about it if you consider this thing on the whole category, because it's, as you say, very infinite dimensional space. So it's maybe more reasonable to. I'm going to describe the functions on this space now, so at least you will know what the functions are. And it's maybe easier to think you take a particular motif M, you consider the Tanakian category generates. So you restrict everything to M, and then you find something inside affine space of dimension n square, if n is the dimension of your motif. And you should think that you look at the period metrics, you write the equations coming from geometry, and then you consider these equations, and then these equations will define this. So for example, if you have an elliptic curve with complex multiplication, then you know that, so here you have one period, here you have the other. So you know that x11 is equal to tau x12. And there's another relation. So you consider these equations, and these equations define your space. Yeah, so the proper way to formulate Grothendieck's period conjecture actually, so this, no, yeah, no, okay, point. Or, yeah, so this is a numerical shadow of the true conjecture, and the true conjecture is that this comparison isomorphism is a generic point. Well, what does it mean to be a generic point? It means that the Zariski closure is the whole thing. And here, the relations that you have put into the definition are those coming from geometry. So for morphisms of pairs, for this boundary thing. So it tells you that there is no other relation that it's satisfied by all periods of all algebraic varieties at the same time. This is what this is telling you. Okay? So what is the relation between these two? So, first, the Zariski closure of something is connected. So first information is that this torsor of paths is connected, a torsor of isomorphisms. And this is already extremely hard to to think about and try to prove anything. And once you know that it is connected, since it is a torsor over the motivic Galois group, the dimension will be that of the motivic Galois group. So it's this extra information plus the numerical information. Okay. And then now I can explain the relation to the Kontsevich-Zagier conjecture. Yes. What is the scheme? It's part of what you prove in the general Tanakian formation, that it is representable. You give the factor of points and you prove that it is representable by something. So it's if you think, as I explained, in terms of well, let's say you take a particular motive, so you are working on finite dimensional things, and you you choose a basis of the RAM cohomology and Betti cohomology, and then you are really working with inside a to the n square, and then it's the structure of closed subvarieties of a to the n square. Okay, so what are the functions here? So this is also some general Tanakian phenomena, that functions are represented by symbols, where M is an object of the category. So this will be a motive over K. And then omega is an element of the image of the object by the first 5 factor. And sigma, so you will see the letters are not randomly chosen. So sigma is an element of, so you consider the image by the second 5 factor, and you take a dual. Okay. So this is the ring of functions is generated by this thing, and modulo the relations coming from morphisms in the category. Okay, but now, so we have this ring of functions, but we also have a complex point. So you can consider the evaluation of the function at this point. Okay, so evaluating, so I mean, abstractly, you can do this for any point of the torsor, and this means, so you take the point, So the point is an isomorphism from omega de Rham to omega Betty, tensor C. So you apply it to your class omega. So you get something in omega Betty dual tensor C, and you pair it with the element sigma. And this gives you a complex number. Okay, so now comp is the comparison isomorphism given by computing integral. So this complex number is the integral of omega along sigma. Okay, and what does it mean that a point is generic? It means that the evaluation map on this point is injective. Okay, so this was exactly the Kontsevich-Zagier conjecture. Yes. Mm-hmm. Well, you consider first you consider the vector space generated by the symbol. You need to mod out by all relations coming from morphisms. And then you need to define the product, and the product is given by the tensor product. So if you have two things, you will consider the object M times M prime, and omega times omega prime, and sigma times omega sigma prime. Okay, so, and yeah, so let me just add one comment, is that, well, I told you we wanted to have a Galois theory of periods, and you have a Galois theory of these objects. Well, Galois theory means an action of the motivic Galois group, and the action is just given by composing with your given automorphism. So if you assume that the conjecture is true, this means that this action goes through the evaluation map, and then you get this Galois action you wanted on periods. Okay, so this is what I said, that you need to know that this thing here is independent of the way you write your integral, and then these are exactly the relations by which you mod out. Okay. Any questions? Okay, so now it's clear that I'm not going to finish my lecture. Well, what should I say? So, okay, so let me tell you what you can prove in this direction. So you can prove aversion over function fields. Okay, so very roughly speaking, so this is a conjecture about the transcendence properties of numbers associated to a given variety. And what we are going to do is we are going to consider a family of varieties. So for each point in the base, you will get a period number, and this will glue together to a period function. And then you can try to compute the transcendence degree of these functions. And the first thing you can expect naively is that it's not in the Blackboard anymore, that this is equal to the dimension of the motivic Galois group. But you see very quickly that this is not going to be true. So example, so now you consider a family of elliptic curves. Okay, so now we are going to K is equal to C. So this is purely geometric. We are going to work over the complex numbers. And you can consider a family of elliptic curves. And yeah, so for each elliptic curve, you know that the motivic Galois group is equal to, well, you know what it is, and for most of them, it is going to be GL2. So the generic one is GL2. But if you consider the periods as functions, you still have the relation that the determinant is equal to 2 pi I. And this is, 2 pi I is a very interesting number if you work with numbers from the point of view of Q bar. But from the point of view of functions over the complex numbers, this is as interesting as the function 1. So this is just a constant function. Okay, so this is a relation. This is a relation that we don't have here because 2 pi I is algebraic, but that you should consider here. Okay, so you need to deal with the fact that the determinant is constant. And then this is constant equal to 2 pi I. And there are various ways to think about this. So if you like differential equations, for example, these period functions are going to satisfy a second order differential equation. And this determinant is the Wronskian of the differential equation. So if you think in terms of differential Galois theory, this will tell you that your group is inside SL2. Okay, so what we should expect, and you can also imagine that there is nothing else that is going to be a constant on all the family and exist on all fibers. So this heuristic suggests that the group you should get is SL2. Okay, and it is true that the transcendence degree of the functions is equal to 3. So I think this was proved by Igusa. Or well, you can also prove it in working with modular forms in relatively elementary terms. Yes. I'm going to define it. So I'm just trying to explain that it is not going to be GL2. So yeah, let me explain how you get the group. So function field version, I said. So it means we are going to work with big K, which is the function field of some algebraic variety over the complex numbers. So S is a smooth, connected, complex variety. And then I'm not going to enter into the details of the construction, but there exists a category of Nori motifs over this big K. Okay, the idea is the same as the way we constructed the category over a subfield of C. So you are going to work with, you are going to consider this quiver of varieties over big K now. And what I need to tell you is what is the quiver representation. Okay, so the quiver representation before was taking a singular cohomology of the pair of varieties. So now the analog of singular cohomology should be a local system. Okay, so you can take a model of your variety over S. You choose a model. So you know that on some open subset, this will be a locally trivial fibration, and then the direct image will be a local system. So you want to take a fiber of this local system on some point. Okay, and the subtlety is that you cannot choose any point, because we want to do this for all varieties at the same time, and for every point of S, there will be some family which is singular at this point. Okay, so what you need to choose is a generic point. So in some sense, I mean, So I'm just going to say this fiber at a generic point. So there are several ways to do this. You can work with tangential base points or with smaller and smaller neighborhoods that go one inside another. And well, once you've set up this properly, you get your quiver representation, and you run Norris machinery, and the geometric ingredients are still there, and you get your Tanakian category. And then, so let me call it M big K. There's something you can always do is to take a motive over the complex numbers in the previous sense, and consider it as a constant motive over the function field. Okay, so in this way, you get a map from motives over C to motives over capital K. So this is like a constant motives. And you also have this, so before we had the Betti realization factor to vector space over Q. Now we have this more complicated thing, which gives a generic local system. So well, this is notation local system over eta. So you imagine a generic pointer. So the objects here are pairs U. So U is a Zariski open subset of S. And L is a local system on U of C. Okay, and then you mod out by the usual thing if on a smaller open they coincide, it's like a germ of a local system, like you do for sheaves. Yep. So you have a map here, which is the Betti realization map. And then the theorem you can prove. So this is something, well, that in this particular form I prove with Peter Jossen. But it's in a different form. It's in the work of Ayub, and well, later in some cases by Ivan Rey. Is that this? So you have two functors of Tanakian categories. They will induce functors on the representations of, well, these are categories of representations of groups. So they induce functors on the groups, and these functors sit into an exact sequence. So in the middle you have the motivic Galois group of big K. So the constant motives functor will go to the motivic Galois group of C. This map is surjective. And then you get the motivic, the Tanakian group of local systems over eta, which is, well, you should think this is a kind of a limit of the algebraic completions of the fundamental groups of all Zariski opens. Okay, so a way to think about this group is you consider your variety S, you take out all complex points, and then you take the fundamental group of that space. Okay, yes? Are you asking about what comes here? Yeah, so these categories here are the representations of those groups. So this is the one we constructed yesterday, and this is the one that goes here. So this category will be the representations of some group, which is the motivic Galois group over the function field. And what I'm saying is that this map induces a reverse map in the other, between these categories, between these groups. Sorry. So what you get here is something like a fundamental algebraic group of the generic point. Okay, this is something that you sometimes call the algebraic fundamental group of the function field K. Okay. So the theorem is that this is an exact is an exact sequence. Okay, you should notice that I didn't put 1 here. So this map is not injective. And this is related to the fact that the local systems that are controlled by this object are those that come from geometry. So more or less injectivity of this map would mean that everything comes from geometry through subquotients and so on, which is not true. Okay. So yeah, so let me make a few comments. So this is well, this is a summer school on Hodge theory, and this is a motivic version of a fundamental result of Hodge theory, which is the theorem of the fixed part. This is a motivic version of the theorem of the fixed part. Okay, what does the theorem of the fixed part say? You consider the category of variations of pure Hodge structures on some base S, and see, okay. Oh. Tra 5 minuti ho finito. Okay. Mm-hmm. Hmm? I think so, yeah. Yeah, I think should be I think it's the unramified Galois group of K over C, something like this. So it's very closely related to the Galois group of function field, but you don't see you only see the generic information, well, which is reasonable because it's the function field. It's maybe just the Galois group of the function field, right? I'll have to think so. It's either the whole thing or a quotient that you can identify. It's okay. Yeah. So I was telling you what the theorem of the fixed part is. So it's the same situation where you consider variations of Hodge structures, so pure variations, and there's something you can always do. If you have a Hodge structure, you consider it as constant over the family. And then, as you learn from Bruno, a variation is a local system plus something else. So you can forget the something else, and then you get a local system. And the theorem says that So if you consider a variation of Hodge structures such that the associated local system is trivial, so a sum of copies of the trivial representation of the fundamental group, then it comes from a Hodge structure. So the only way trivial local systems arise are as constant variations of Hodge structures. And this is the kind of main, if you translate this back to groups, this is like one of the main ingredients that goes into the proof of like, this is exact in the middle. You need a bit more, but it's like the main thing. Okay, and then the corollary of this, which is the reason why I'm talking about it, is that now you can consider the transcendence degree of the field generated over the function field by the period functions of a motive. And then this is something you can compute using differential Galois theory. So this is actually, so here you have a local system, but you can also go to a vector bundle with connection, which is the Gauss-Manning connection. And it is, I mean, one of the fundamental results of differential Galois theory is that this transcendence degree is the dimension of the differential Galois group. And you have a comparison between these two. This is the version of the Riemann-Hilbert correspondence. Now I say it, and then this will tell you that this transcendence degree agrees with the group you get as a quotient from this one. Okay, so this is not exact here, but if you take a particular motive, then you get you get a quotient here, an injective map here, okay? Because this one comes from geometry. And I'm inventing random notation now, so it just means you take an object and you realize everything, and these are the corresponding quotients. Okay, so what you know is that this transcendence degree is equal to the dimension of this group, and by differential Galois theory. And then what the exact sequence says that is that the dimension of the group of this group is the dimension of the kernel of the map. And this kernel of the map is what you would like to call the relative motivic Galois group. So it's the motivic Galois group of your motive over the function field, except that you mod out by everything constant coming from the base field. And that's it, I guess. Thank you. Yeah, so in tomorrow I would have finished the lecture from today, and the next half an hour is the explanation of Ayub's approach to this question. So there's another way to construct the motif fundamental group, and with this other way, you can also prove a functional statement that is not in this form. So this form is the Grothendieck version, and you can prove a very precise and very surprising statement in the shape of a Kontsevich-Zagier conjecture. Any questions?
Just a comment. So it's not the Galois group because it would be with étal. I mean, pi1 étal of this one should be the Galois group.
Yes.
But when you put alg, it means the pro-algebraic completion?
It's the pro-algebraic completion, yeah.
Yeah, so there is a...
But they are very closely related to each other.
Yeah,
right?
yeah, and should factorize.
Yeah, yeah, this is...
You can probably put Galois group at the place, even it's different.
Yeah, so
factorize. Any questions?
sorry, so that last comment you made, like the pi1 is the actual motivic Galois group, and then it's not pi1 alg. That's the that. Oh, it's
yeah. So you you can consider K as a variety over C, and then take the étale fundamental group of that. So this is the Galois group of the function field over C. So this is the étale version, and this is more. So you, for example, for the fundamental group is just a group. So it is not the Tanakian group of anything because it's not algebraic. So when you see it in the Tanakian setting, what you do is you take the pro-algebraic completion, which means you consider all representations of this and in finite dimensional representations, and you take the Zariski closures of the image of all those. So you get a bunch of algebraic groups, and then you consider the limit of all of them. Okay, and the étale is also a limit of this kind, and the two of them are related. I think there is a map, yeah. Yeah. The map goes from. So it's a projective limit, so it will go to the algs will go to étale, I think, no? Is it the other way? Okay. Well, you can put a question in the box, and then I will think about it.
So is it possible to like are these computer like if I like could you compute an example of the pro-algebraic completion of some group, like say a Z, or is it?
Yeah, the thing is it's very big, so. Yeah, so X means exercise. You take well. Let me repeat what I said. So, well, you take a group. When a group is just a group, you sometimes call it an abstract group. Okay, so it means there is no extra structure. So, so then the category of representations of G is a Tanakian category. So it means it's the representations of some affine group scheme. And then this one is called the pro-algebraic completion of G. Okay. And there is, so well, this is one way to define the pro-algebraic completion. But explicitly what it is so you consider representations of your group. And for each one, you take the image and the Zariski closure. And then, well, you can order this by inclusion, and then you take the limit of all this. Okay, so if you want to compute this for Z, well, you should understand what is a representation of Z. So this is a vector space with an endomorphism, and then try to compute this, and then you will see that it's quite huge. And so there's something that it's a bit well behaved, which is the unipotent, the pro-unipotent completion, where you do the same thing, but you take unipotent representations. And if you compute that one for Z, this will be equal to the affine group.
Javi,
Yes.
I was still confused about this question about computing. So you had E, an elliptic curve, took M to be H1, and then you stated that the endomorphisms are equal to the endomorphisms of the elliptic curve tensor Q. And somehow I'm happy with that in general motive land, but yes. Are you just doing something in motive land, or you're actually saying this is a fact in Norrie motives and we could prove it with some?
I guess it's a thing in Hodge structure land. So So these are the endomorphisms that of Hodge structures.
So we could convince ourselves of that, given the material that you've done.
On Hodge structures, yes, I think you can do that, and then yeah, I imagine I was implicitly, well, as I said, yeah, I try to answer Bruno's question, saying that you cannot get rid of Hodge theory, and yeah, so I guess you need to know that the endomorphisms of Norrie motifs are the same as of Hodge structures, and then use that computation. Right. All these are like weak forms of the Hodge conjecture, so that are known. Yes, so. Mm-hmm. Yeah, you don't really, I don't think you can do it that way, that explicitly construct. It's more you prove that there is some kind of polarization. So like essentially what you try to prove is that the polarization that gives the result for Hodge structures is motivic. And then it will give the result there also. Yeah, thanks for the question, because it's something I really wanted to say. Is that one Norris category is very nice to get the motivic Galois group, and the objects are quite easy to work with. But the main problem with this category that is showing in all your questions is that we have no idea of what morphisms are. There's no description of the morphism groups. So one of the things you would expect from a category of motifs, since Grothendieck's first ideas, is that morphisms are related to algebraic cycles in some way or another, or at least to some geometry. And to give you an idea of the extent of our ignorance on this question, so you remember the example of GM with respect to 2 points. So we had the matrix 1 log t 0 2 pi I. So I explained that this was an extension of q minus 1. So this 2 pi I by q0. Okay. So you get a map from k star tensor C, tensor Q to this that sends t to the extension given by this H1GM 1t. And in a reasonable theory of motifs, this should be an isomorphism. Okay, and this is something we don't know how to prove in Norrie motifs. So yeah, we don't know how to compute this group, and this is the easiest thing you can try to compute. So we don't know how to compute any group of morphisms. And the advantage of this approach that Ayub uses, which is based on Voevodsky motifs, is that you really know what the morphisms are. The problem is that you can construct a Tanakian category, but you don't know what's the relation of that category with the thing you started with.
Sorry, so do you have, like, is it known that Ayub's category is equivalent to Norrie's category, or no?
Well, the literal answer to your question is no. So I just take 30 seconds. So Ayub, Voevodsky, so they construct this a triangulated category that in Ayub's wall is called DA et al. KQ. Okay? So this would have been the second half of the lecture. Sorry. So this is a triangulated category. From this, he constructs a group in a very nice way. So he gets a group, what I'm going to call G mod K a cube. And then you can consider the category of representations of this group. So this category is known to be equivalent to Norris. This is a theorem of Galois. And what is not known is what is the relation between these two. So the expectation is that this is the derived category of this one, but this is not known at all.
And if you look at the representation category of Ayub's group, is it is that work? Like, can you work with that instead of the derived category, or like is there a reason you can't work with this representation?
Well, it depends what you want to do. To study periods, it's quite useful to work with this category, but here this is a category of shapes, so it's extremely easy to write down objects. Here is much more complicated to write down objects.
So in the function field case, is there a connectivity statement analogy?
There should be, right?
Yes.
Yeah, I didn't think about it. I should think about it because it's maybe something you can prove in this case. Yeah, absolutely. I don't know.
Other question, quick question? Okay, well,
Café.
You have the question box anyway. So let's thank Javier for his very nice resolution.
Thank you.
Okay, so this will be Bruno's last lecture on.
Too bad. Okay, yes, so let me recall where we are. So at the end of the last lecture, so I tried to take another point of view on variation of abstraction, namely functional transcendence. So let me recall the setting. So we had some algebraic variety S, and then I was interested in emulating some kind of algebraic structure on the universal cover. And for doing this, I can take, for instance, any map to the identification of some algebraic variety X that would be holomorphic and by one of S an equivariant. And of course, a typical example would be for variation of our structures. And I want to think now that I'm emulating an algebraic structure on the universal cover through X, through the algebraic structure on X, and I want to compare the algebraic structure on X and the one on S. And so we had a few examples which were, well, you have the multiplicative group. If you take the identification, then this is C star to the N. And here you have exponential, let's say I put a normalization. And here the diagram is just, well, the affine space unidentified. I can do the same thing, same diagram upstairs with a Billion variety. And I have Shimura varieties. So here I take a bounded symmetric domain. I take its compact dual, which is a flag variety. And then here I have a Shimura variety unidentified, which is of the form quotient of a bounded symmetric domain by some arithmetic lattice. And then finally, of course, the most general instance of those things, which actually covers all of them if I were to go in the mixed Hodge structure setting for mixed period mappings, would be any algebraic variety S, take the universal cover, take a period map to D inside. And here I put inside the compact dual, so I can directly look at this. Okay. And I explained that this way, with this format, you can define what is an algebraic variety in the universal cover. It's just the intersection, I mean, it's just a preimage under this map, like call it F, of something algebraic here in the universal cover, and take a complex analytic irreducible component of that. This is what I call an algebraic subvariety of the universal cover. And then I say that something is bialgebraic. So if I take an irreducible algebraic subvariety of S, I will call it bialgebraic. If when I take its preimage and then I take one irreducible component in the complex analytic sense, it is algebraic upstairs. Yeah. Yeah, so I'm assuming that there is a representation into the automorphism of X, the algebraic one. Okay. Which is typically what happens in all those cases. And of course, for the theory to be interesting, you ask that this representation has infinite image, because otherwise this means that actually this map descends to S or to some finite cover of S. And then basically this is the same. I mean, this comes from an algebraic map, so this is not interesting. Okay, so what were the bialgebraic guys? Here it was the translate of subtori. Here it was a translate of abelian subvarieties. Here it were the weakly special subvariety in Chimois varieties, and more generally here, what I defined as being the weakly special subvarieties, which were a generalization of those special varieties, which were the components of the Hodge locus. Okay, so this was the first step, understanding what were the guys with minimal transcendence properties between the covering and the projection to the base. And then we had this X-Lindemann. Maybe I will put it here. So X-Lindemann statement, which was saying that if you take Y inside the universal cover, algebraic, then you take the image and you take the Zariski closures, and this is bialgebraic. Okay, so this is kind of easy to visualize, so that's kind of nice. So here in this case, you take an algebraic subvariety of C to the n, you push it by the multi-exponential to your torus, take the Zariski closure, then you get a translate of a subtorus. Same thing here for abelian variety. And here it's also nice. I mean, it has you take something algebraic here, put it back under the period map, take one irreducible component, push it down, take Zariski closure, then you get something weakly special. Okay. So just a remark about the terminology. As I said, I mean, the result in this case and that case was proven by X. And in that case, you see that this is a functional analog of Lindemann theorem. Lindemann theorem will tell you that if you take algebraic numbers, so in q bar to the n, which are q linearly independent, then the exponentials are algebraically independent. Okay. So hence the name. So this is nice. There is a much more powerful version of this, which is more useful in applications, which is what is called X-genual. And which is related to atypical intersection. So let's see the setting. So the setting is the same. It will tell you the following. Suppose you take, the idea is that you really want to compare those two algebraic structures here, so you work in the product. Except that in this general setting, it's in some sense easier to work as follows. So it tells you that if you take something in S times the universal cover, which is algebraic for the product structure that I did define, okay? And I take U as being the intersection of W with, let me define it this way. I would put it delta, and I take one irreducible component where delta is the graph of the projection. So pi was here. Well, here I have defined what I mean, that what it means to be algebraic there. So here it means that this is the intersection of this with something algebraic in S cross X. And I take an irreducible component. All right, so now I try again. This is an intersection. So typically it should have an expected dimension. Suppose it is not typical, namely it satisfies the following condition, that when you take the codimension of the intersection, it is strictly smaller than the expected one, so the sum of the codimension. Still a problem, or no, it's okay. Then there is a good reason for that. This is what Hodge Theory tells you. It tells you that if you're in this situation, that actually the projection of U in S on the first factor is contained in a strict by algebraic subvariety. Of S. So this is maybe more difficult to visualize what it exactly means, but it's an atypical statement that tells you that if your intersection does not have the right expected property, actually there is a good reason for that. Namely, it lives over something which is bialgebraic. Okay. So as you can imagine, this Hodge-Theory was proven by Axe in the first two cases, for the case of tori and abelian varieties. And it was proven by Mock, Piller, and Zimmerman in the case of Shimura variety. And so let me repeat this statement in the general case of variation of attractor. So this is the following theorem that I call Hodge-Theory for VHS. And so I conjecture it in 2017, and it was proven by Becker and Zimmerman. In 2019. So it says the following. So here it's a bit maybe more visual to see, just because in that case, this triangle has a completion to a square. So you can write this as follows. So suppose you have a variation of a structure. Consider the following period map. Then this time you take something really algebraic in S cross D check. Then you take the intersection U as being the intersection of W with delta, but here you can just write it, if you prefer, like this. And you see it inside S cross D check. And then you have the same conclusion. So if the codimension in S cross D check of U is strictly smaller than the codimension plus the codimension, and here it's maybe easier to visualize because the codimension here is constant, so S cross D hat of S cross D, yeah. Then the projection of U is contained in a weakly special subvariety. And actually, this is this statement, which is much more powerful than axiom demand, that is really useful. So I just want to say that axiom demand is a special case where you take W of the form, well, maybe I will write it here. So axiom demand is a case where you take W of the form pi of y zar plus y for y in d hat. So you see this very special shape, product shape. All right, so you need some time to try to get a feeling of what it says, but it's really very powerful. So what I was planning is trying to give an idea of the proof, but just much too long. So I would just give a flavor of axiom demand in the simplest case, the case of an abelian variety. So as I said, it was proven by Axe using differential algebra methods. But what I want to do is to use tame geometry. Yeah, so maybe I should make some comments for the full story. So this theorem, the proof uses tame geometry, obviously, Pila-Wilke theorem. But actually, there is also a differential algebra proof of that. And combining both, actually, you can see that what was explained by Javier before can also be deduced from some version of actioner. But a more elaborate one than this one. All right, so as I said, what I want to do now is to give some flavor of o-minimal proof of axiom demand, let's say, for abelian varieties, where this is much simpler than the general case. But at least you will see how Pila-Wilke works. Yeah. Yeah, that the function field analog of the period conjecture is essentially a version of X general, but for the total space of the variation of a structure, not for the variation, not for the base. So you have to consider, you have to replace S by the total space of the variation, and so on. So this is a recent preprint of Baker and Zimmerman. All right. So so tame geometry in action. A proof of axiom demand for abelian varieties. So maybe not the full proof, but at least how it works. So recall the setting. So we have an abelian variety A, and we have its universal cover of its identification. Let's say it's dimension n. So this is a uniformizing map. So this is Cn, not gamma, where gamma now is much simpler because it's just z to the power 2n. And for simplicity, okay, I can always decompose up to isogeny An as a product. So for simplicity, I will assume it is simple. Okay, so no non-trivial abelian subvarieties. So now, what do I want to show? I want to show under that setting that suppose I take y inside C to the n, algebraic irreducible, and not a point, so dimension of y strictly positive. Then the statement is that when I project y to An, take the Zariski closure, it should be the translate of an abelian subvariety. But here I'm assuming that A is simple. So what I'm claiming is that the projection, and I take the Zariski closure, should be everything. So I want to show that this guy is A. Okay. All right, so the first thing I do is that without loss of generality, I can assume that Y is maximal among all the algebraic subvarieties contained in the preimage of pi of Y. Okay. So without loss of generality. So let me call this Zariski closure. I will give it a name. Let's call it V. Okay. So I can assume that is maximal among the irreducible algebraic subvarieties of Cn contained in pi minus 1 of V. Right, because if it is not, then I replace by a maximal one containing Y, and this is the same statement, so I did not lose anything. All right. So now that I'm in this situation, what can I do? Well, the strategy is the following. It is enough to show that the idea is to use the group gamma. So if I want to show that the Zariski closure of the projection of Y is the full A, it is enough to show that the stabilizer of Y what is in Cn of Y is positive dimensional. So this stabilizer is an algebraic group. So here you see that I should be more careful in the notation, but I'm a bit lazy and I don't have much time. You see that here, this Cn is really thought as a group of translation. It's not the universal cover itself, but the universal cover itself acting on itself. Okay, so this is really a group here. Okay, and this is where the tame geometry will take place. It will not take place in the space or in the universal cover, but essentially you want to apply Pila-Wilke in the group of photomorphism. All right, so if you prove that this group is positive dimensional, then what you get is that pi of Y zar is stable under the projection of that group zar. But that group will be a subgroup of the Euclidean variety of positive dimension, so it will be A, because A is simple. And then, of course, this Zariski closure is stable under the full group, so it is the Euclidean variety itself. All right, so we are reduced to that statement. And now you see that we are not far from Pila-Wilke. We want to prove that a certain set actually, certain algebraic set actually is positive dimensional. So how do you do that? Well, you have to choose a fundamental semi-algebraic set for the action of Z to the 2n on Cn. But in that case, this is very simple. So semi-algebraic fundamental set for the action of gamma on C to the n. So you take, let's make a picture. So of course, this is my picture of C to the 2n. Maybe I should do that this way. I will choose this fundamental set. Okay, so this is my F. So this projects on my Euclidean variety. And I'm just asking, acting there by translation and gluing. So now inside this guy, I have my guy V here. So let's suppose for simplicity that V is not the full A. So I can make this kind of picture. So I don't know exactly. So V will cut this fundamental set somewhere. I can always choose a fundamental set such that the intersection is not empty, because up to translation, I'm covering everything. So I get that thing here, that two-dimensional thing, cutting this big three-dimensional cube. And inside this, so this is pi minus 1 of v. So of course, this is analytics. This is very disgusting. This is very complicated. I'm just making a local picture, okay? And inside that guy, I have y, which is algebraic, nice and clean. Here, okay. So how do we argue? And we want to show that the automorphism group of y is positive dimensional. So let's be optimistic and just define sigma of y as being the set of elements in the group, in that case c to the n, such that when I translate a bit y by an element, then I'm still intersecting the fundamental set. So you see, I want to push this y by my element g, but I call it z, okay? A little bit. I push it a little bit. I want it to still intersect the fundamental set, and of course, I still want it to be contained in the preimage of v. So I want that y plus z is still contained in pi minus 1 of v. All right, so if you write this in a simple first order formula, we'll just write that the dimension of y plus z intersected with the fundamental set intersected with pi minus 1 of v. So now I'm taking this intersection. Sorry. Okay, sorry, thanks. Not empty. So I want this to be equal to the dimension of y. Okay. So in other words, I'm asking that when I push a little bit my y by this element z, well, so I get just the translate, and I want that I get something of the same dimension, still contained in pi minus 1 of v, and still intersecting the fundamental set. Okay. All right. So now, what is the point of writing this way? Well, what we know is that the projection pi. So of course, it goes from the universal cover, in that case, c to the n to a n. So this is not definable, but what we know is that in restriction to f, then this map is definable. So this means that that set, because that set is definable, and this dimension function is actually a definable function. So this formula defines a definable set. So this is actually Rn definable. This is where abelian varieties are much simpler. There is no exp, just Rn. All right. So now, if I want to, what I want to show, well, for me, it's enough to show that that guy is positive dimensional. Or rather that it contains a positive dimensional algebraic subset. So if sigma of y contains a positive dimensional semi-algebraic set, we are done. Right? The reason being that by maximality of y, if sigma of y contains a positive dimension, when you apply sigma of y to y, you still get something semi-algebraic. If that guy, start again. Take this positive positive dimensional semi-algebraic set in sigma of y. Okay, then apply it by translation to y. Then it is still contained in pi minus 1 of v. So it complex Zariski closure still also, because it's complex analytic. And this guy is semi-algebraic. So this means that if that guy contains something positive dimensional, then I would get, so let's call this guy W. Indeed, by maximality of y, I will get that y plus w is equal to y. Okay. But then this will imply that theta y contains w. And so it will be positive dimensional because it will contain this positive dimensional semi-algebraic set. Okay. So that's the maximality. I should write it this way. Okay. So we are reduced to proving this, and this is where we apply Pila-Wilke. This just because, okay, so it's a small exercise. I'll let you think about that, but there is no problem. Okay. All right, so how do I apply Pila-Wilke? So I have to prove that this sigma of y contains something semi-algebraic positive dimensional, so I just count points. Namely, I intersect with my lattice z to the power 2g. So now let's look at what is this set. So now I'm looking just as a set of elements in gamma satisfying those properties. And if you look at it correctly, you are just counting elements of gamma such that actually when you translate, you still intersect f. Okay. So you see now what happens. I'm taking this y, but you have to think that this y is going to infinity. And so now I'm pulling back y from infinity by very big elements of gamma so that I intersect the fundamental domain f again. In other words, so what is the claim? The claim so maybe it's clear to say it this way. You can just look at elements of gamma such that when I'm just counting the number of translate of f under the fundamental group that still cut y. Okay, it's the same thing as saying. Okay, maybe that's clear that way. So now you see what is the picture. Let me make a two-dimensional pictures rather than my cube, because otherwise I would be lost. And basically what I have my y, and I want to count the number of fundamental sets that I'm cutting with respect to the height of the translation. So now let's look at this. In the Pila-Wilke theorem, you just have to count the z in gamma, which is z to the 2n, such that y intersected with z plus f is different of the empty set. And now you want that the height of z, this element in c to the g, is smaller than t. And I want to count that. Now, what is the height in this picture? Well, the height of the picture is just the L infinity norm of the element, right? If I fix the origin as being here, then each time you cross a boundary, you increase the height by at least 1, either on the abscissa or the ordinate. Okay, so this thing is just the L infinity norm of z with respect to the basis. Okay, and so you see that this thing is at least t. Maybe t over 2. Well, depending on the dimension, but on that picture, it's t over 2, I think. And so this is at least a polynomial. And so I apply Pila-Wilke, I'm done. So the conclusion of Pila-Wilke is that sigma of y contains some positive alge is not empty. So sigma of y contains a positive dimensional semi-algebraic set. Okay, that's the proof. So you can imagine that for Shimoa variety, you try to do essentially the same proof. Now the fundamental set is of course more complicated, but still reasonable. This is given by Ziegler sets. What is much more complicated is that now gamma is your arithmetic lattice in a non-commutative group. So you have to consider the height, consider what is balls for a given height. And this is complicated, but you compare it to balls for the usual distance in a bounded symmetric domain. And there, what plays this role that you get a polynomial estimate is basically non-positive curvature. So you have exponential divergence of geodesics, and basically this will give you this polynomial lower bound with respect to the height. One remark is that for variation of a structure, I don't know of any proof of action in demand without action annual. So everything is proven directly. I don't see a proof independent of action annual, and this is more complicated. Okay, so now I can start my last lecture. Are there any questions about that? No? Okay, so the last topic I want to talk about is atypical intersections. So in the first lecture, I stated a result with Baldi and Ulmo about the fact that the Hodge locus of positive period dimension for variations of Hodge structures of level at least 3 is algebraic. So I was hoping to have time to give a proof, at least a sketch of the proof. I won't have the time, but what I will have time is to explain the heuristic. So basically the question is that, so you have the Catani-Deligne-Kaplan theorem that we proved using o-minimality that says that this Hodge locus is a countable union of algebraic subvarieties. So after this theorem, most natural question is to ask about the distribution of the special subvariety. For instance, you can ask, suppose you have a variation of a structure, you have this countable union of algebraic varieties. Can you describe this, the Zariski closure of this countable union? Is there any nice property for this? And well, let's take examples. So suppose you take the universal family of abelian varieties, and there we prove that the Hodge locus here, so V now is R1 F lower star Z. So we have seen, I already explained that this is dense even for the usual topology. So the Zariski closure a fortiori is the full space. So, but now you can ask the same question for a subvariety of AG. And you restrict the variety. So you have just a family of abelian varieties, of principally polarized abelian variety. So now the Hodge locus for S with respect to the same variation, of course, this is nothing else than the Hodge locus of AG for the variation intersected with S. And here, even if you know that that guy is dense in AG, it's absolutely not clear what happens when you take this intersection. It could be whatever it is. Okay. So the idea is always the same, is that it is easier to understand the Hodge locus of positive dimension. So let me define it again. So this is the union. Of course, this is still countable union, but countable union of special subvarieties of positive period dimension. So the special subvarieties in S whose image in D mod gamma as positive dimension. And then the first result we obtained with Anya was under the assumption that the generic Mumforte group is simple, at least it's a joint group. Then we got this alternative. Then either this Hodge locus of positive period dimension is algebraic on the nose, or it is Zariski dense in S. So it was kind of surprising, because when I started thinking about that, I thought that you could basically maybe realize any kind of algebraic subvariety of S as being the Zariski closure of the Hodge locus. So of course, I will not give the proof, but the main ingredient is Ax-Lindemann for a variation of Hodge structures, plus an independent algebraic statement. So now, of course, the main question when you see this result is how to decide in which case you are, right? And this is where you think of Hodge loci again through period maps as intersections, so as atypical or typical intersections. Namely, you have this period map, and suppose I have a special subvariety Z. So this is the preimage of some period subdomain, take an irreducible component inside S. Then I will say that this special subvariety is atypical. Well, if the intersection is atypical, because if the codimension of phi of Zn in D mod gamma is strictly smaller than what it should be, namely the codimension in D mod gamma of phi of S plus the codimension in D mod gamma of dz mod gamma z, right? That guy is obtained by intersecting the image under the period map of phi of S inside D mod gamma with dz mod gamma z. So it should have, if it is typical, it should have codimension should be the sum of the codimension. And I will say it is atypical if it is not. And so otherwise, we say that Z is typical. So you get that your Hodge locus is actually a union of the atypical locus and the typical one. And now, if there is a justice in this world, atypical should be rare and typical should be most of the cases and happening a lot of time. So the conjecture that I call Zilberpink for ZVHS. So I made in the same paper, I conjecture this actionuel. I also conjecture this Zilberpink for a variation of Hodge structure. And actually, I was too careful. So my atypicality condition was stronger. So we corrected that in the last paper. So this is really now this condition that we corrected with Baldi and Ulmo. It says the following, that the atypical locus is always algebraic. So it's rare. And the typical one, well, either it is empty, or it is dense for the analytic topology. Okay, so this makes very precise the alternatives that we get for the positive dimensional part. So in particular, this conjecture implies, so this is called Hilbert-Pink for a variation of a structure, because in the special case of where S is a Shimura variety and you look at the canonical variation of a structure on it, you recover conjecture of Hilbert and Pink. And well, there are many interesting geometric corollaries, but let me just mention an arithmetic one that you can call André Hort for variation of a structure. So that I will also conjecture in 2017. That says the following: suppose that you have a variation of a structure that contains a Zariski dense set of CM points. Of CM points for S, for the variation V, then actually this can occur if and only if S is essentially a Shimura variety. So this means that the level of V has to be 1. So this implies that D mod gamma is the identification of some Shimura variety. And second, this should imply that the morphism, the period map, which in that case would be algebraic, is dominant. So of course, if you are in this situation, CM points are dense because they are dense here and this morphism is dominant. But this should be the only case. And this is implied by this. It's not very difficult to show. The point being that, of course, CM points are in the Hodge locus and they are atypical for any variation which is not of that type. Okay, so now I can state more precisely the theorem with, so now you have the heuristic, and you see that the heuristic is very simple. It's just a question of intersections of subvarieties. Yeah. No, it's for general variations of attractions. CM point, yeah, maybe I should have said that. CM points in the abstract setting just means that the Mumford group is a torus. So it's as small as possible. Sorry, I should have, yeah. Yeah. Is that what? That the atypical locus is? The atypical one. I will come to that. So what is the theorem now? So with Baldi and Ulmo, the first thing is that suppose, so there are well, there are many independent parts, but let me summarize it this way. Suppose that the level of V is at least 3, then actually the entire Hodge locus is atypical. Right? So this is kind of very surprising. It tells you that the Hodge locus should not exist as soon as the level of the variation is at least 3, because all the special subvarieties in that case, they are necessarily atypical. Okay. And the second part of the statement is that suppose in addition, so still level larger than 3, suppose in addition, well, yeah, that G add is simple, well, maybe I shouldn't put in addition. Suppose that Jihad is simple. So this is a different set of assumption. Then the Hodge locus atypical is algebraic if I consider only the positive dimensional part. Okay. So if you put the two together, you recover the theorem that I stated first, which was suppose you are in level larger than 3 and that the adjoint group to the generic Mumford group is simple, then the entire Hodge locus is atypical. In particular, the entire Hodge locus of positive period dimension is atypical. So this guy is actually the Hodge locus of positive dimension. And so it is algebraic. Right. So this implies that if you have level larger than 3 and G at simple, the Hodge locus of positive dimension is algebraic. Okay. So the main, so that answers the first part of the conjecture. So now, and I already explained the statement for hypersurfaces, but I maybe still have the time, yes. But maybe I want to give an idea of this. Actually, this is very easy. And this is the main point I've been missing for years, but it's trivial. And this comes from Griffith's transversality. So let's look at the picture again. So we have this period map. Now here I take d prime mod gamma prime, or if you want dz mod gamma z. And what I'm taking is actually just the intersection of this. So I should say it makes sense because phi can be assumed to be proper. So this is really a complex analytic subvariety in d mod gamma. Okay. So I'm intersecting those two complex algebraic subvarieties. And now, what is the typical, so what are we looking at? We are looking at the codimension. So we are looking at Sn, phi of Sn. For simplicity, let's just assume that phi is immersive. Okay. So we are really looking at Sn intersected with dz mod gamma z. Okay. And we are counting codimension. But now the point is that if Z is typical, so what is the condition? The condition should be that the sum of the codimension is equal to the codimension of the intersection, which means that if you prefer, when you look at the Lie algebra of the group defining this guy should contain the entire Lie algebra in all the other pieces because of Griffith's transversality. Typicality forces this because you want the sum of the dimension to be the right one. So now the argument is very simple. I'm just saying that if L is at least 3, and if you have a Hodge-Lie subalgebra inside the ambient Hodge-Lie algebra G, if you have this property, then actually GZ has no choice than being the full Lie algebra itself. And so such guys just don't exist. So it's a purely Lie theoretic statement about graded Lie algebra of that kind. Okay. So if L larger than 3, such this property implies that GZ should be equal to G, which of course is impossible if you want to have a special subvariety. So this is for the first part. So actually, this is completely trivial. And the second part, well, this is X general plus Pila-Wilke again and again. So it's a long and delicate induction, but it was already done basically in the case of Shimura varieties. So we knew how to do that. So here I should add, of course, that this assumption is again to get rid of all troubles that you can get with products. All right, so this answers the first part of the conjecture, at least with respect to the positive dimensional locus. So as I said, what we really don't understand are the atypical points. So what about the typical locus? Well, we almost completely prove the result in that case, but not exactly. So the second theorem in that paper is Baldi and Ulmo is that if the typical Hodge locus of positive, not necessarily positive, if the typical Hodge locus is not empty, so by the first theorem, this implies that the level of V is 1, meaning essentially you have a family abelian variety or 2, then actually we do not prove that the typical Hodge locus, I erase the conjecture, we do not prove that it is dense, but we prove that the entire Hodge locus is dense. For the usual topology. And here it's a kind of not very complicated argument using Hecke correspondence on D mod gamma. All right, so I think I will stop here.
Thank you. Are there any questions? I have a question.
Sure.
In your theorem 1, what do you know when the level is 2?
So there it really depends on the nature of the Mumford group.
So there are counterexamples.
There are examples where
you have some
so the typical Hodge locus can be positive dimensional or it can be empty. So I guess one student of Ulmo is trying to classify all this, but
other questions?
So typically, when you are in a Green-Griffiths situation, for certain family of surfaces, you can prove that the Hodge locus is dense, and this is exactly what I mean. You are in a typical situation because.
Can you give some heuristics on the theorem that the Zariski closure of the positive part of Hodge locus is Zariski dense or algebraic? Like, why not between?
Not really. Okay, so the argument is kind of completely different than this. Well, it uses at one point, crucially, it uses X in the man. But there is an additional interesting algebraicity statement, which is that okay, basically you do the following: you take an algebraic subvariety. How do I want to say that? Yeah, you take an algebraic subvariety in the total space of the of your bundle. And you look at the locus inside this algebraic subvariety where an FP class stays FP for a fixed P. Okay? And what was extremely surprising and was obvious for Anya, but for me it was extremely surprising, is that this locus is actually algebraic on the nose. So if you get the intuition for this, then that's nice. And then after that, this is this argument plus X in demand once you project on the base. Basically, what you prove is that the Zariski closure, what you prove is that basically you prove that the Zariski closure of this Hodge locus, actually you prove that it is foliated by Hodge loci. So actually it was already either algebraic or it was the entire space. This is what I said, but okay. I think this is what I said. You have to press the button because it's down. No.
So the set of classes that remain FP in positive dimension is algebraic.
Yes.
In the above boundary, simply.
But you see the difference is that this is a statement about FP classes which stays FP on a positive dimensional locus, and but there is no integrality. So actually, this statement is true for any I. You don't need to take FP in something of weight 2p.
The statement of essential differential geometry using only Griffith's transversality. So no,
yes, this is another incarnation of Griffith's transversality, but it's yeah.
Other questions? Okay, so I guess let's thank Bruno for his very nice series of lectures.
Thanks.